Hello there, and welcome to Science for Sleep, where curiosity gets cozy and the universe slows down just enough for us to wander through it together. Tonight we're travelling somewhere unbelievably large, so large that even the Milky Way begins to feel small, tucked away like a tiny neighbourhood on the edge of a continent made of galaxies. Our gentle journey tonight is about Laniakea Supercluster, the gigantic structure that contains our galaxy, thousands upon thousands of others, and stretches across more space than the human brain was ever really designed to picture comfortably. It is the enormous cosmic region we drift through without ever noticing, carried quietly through the darkness at millions of kilometers per hour while we sit in traffic, make tea, fold laundry, or stare at the ceiling at 2 o'clock in the morning, wondering why we suddenly remembered something embarrassing from 11 years ago. And perhaps that is one of the strangest things about the universe. The larger reality becomes, the more ordinary our lives continue to feel inside it. Right now, as you listen to this, the Earth is turning beneath you at roughly 1,600 kilometers per hour, depending on where you live. The Earth itself is orbiting the Sun at around 107,000 kilometers per hour. Our solar system circles the center of the Milky Way at more than 800,000 kilometers per hour, and the Milky Way itself is drifting through the cosmos towards something enormous and mysterious deep inside Laniakea. Meanwhile, from your perspective, you are probably sitting still. Funny how that works. Before we settle into tonight's slow cosmic drift, I'd love to ask you something. Where in the world are you listening from tonight? And what time is it in your corner of Earth right now? Maybe it's late evening and the streets outside have gone quiet. Maybe rain is tapping softly against the windows. Or perhaps it's early morning somewhere, and the sky's only just beginning to brighten while the rest of the world still sleeps. There is something oddly comforting about knowing that people all across the planet can listen to the same story, while standing in completely different moments of the day. Different countries, different languages, different weather, yet all of us floating together on the same small planet, inside the same vast cosmic structure. And if you find tonight's journey relaxing, comforting, or simply a pleasant way to unwind after a long day, I'd be ever so grateful if you liked the video and subscribed. It helps this quiet little corner of sleepy science continue to grow and reach fellow travellers looking for calm conversations about impossible things. Now then, let's get comfortable. Lower the lights a little if you can, settle into your blankets, and together, let's slowly zoom outward from the familiar world around us into one of the largest structures human beings have ever discovered. Because for most of history, humans believed the universe was fairly small. Not tiny exactly, but manageable. Ancient civilizations looked upward and saw stars scattered across the sky like distant lanterns. The sun moved overhead during the day. The moon changed shape through the month. The planets wandered slowly among the constellations. Everything appeared organized around Earth, or at least close enough to matter directly to human life. The night sky felt personal. Ancient people gave names to the stars because the stars seemed reachable in a strange emotional sense. Farmers tracked seasons by them. Sailors crossed oceans beneath them. Entire mythologies grew around patterns of light that were actually separated by unimaginable distances. Yet nobody knew that at the time. To ancient eyes, the universe looked intimate. Even after astronomers like Nicholas Copernicus and Galileo Galilei revealed that Earth was not the centre of everything, the cosmos still seemed relatively contained. The solar system became larger, the stars became more mysterious. But humanity still imagined the universe as something finite and understandable. Then the telescopes improved, and that is when the trouble started. Because every time humans built a better telescope, the universe became less emotionally manageable. First, astronomers realized the Milky Way was not just a fuzzy band in the sky, but an enormous collection of stars. Then they discovered those stars stretched across distances so vast that light itself needed years to travel between them. A light year, by the way, is about 9.46 trillion kilometers, which sounds made up. It genuinely does. Human beings invented units so large that they stopped behaving like normal information. After a certain point, the brain quietly gives up and replaces understanding with polite concern. But even after discovering the true scale of the Milky Way, many astronomers still believed our galaxy might be the entire universe. That idea survived surprisingly long. In the early 1900s, scientists argued intensely about strange spiral shapes seen through telescopes. Some believed these spirals were clouds of gas inside the Milky Way. Others suspected something far more unsettling. Maybe they were entirely separate galaxies, entire island universes floating impossibly far away. The debate became so famous that it was literally called the Great Debate, which honestly sounds less like astronomy and more like two Victorian professors dramatically arguing beside a fireplace while holding tiny cups of tea. Then came Edwin Hubble. Using observations from the powerful Hooker telescope in California during the 1920s, Hubble measured the distance to the Andromeda Galaxy and proved something extraordinary. It was far outside the Milky Way. Suddenly the universe exploded in size. The Milky Way was not the universe. It was one galaxy among many. Then many became billions, and eventually billions became part of something even larger. Galaxies, astronomers discovered, are not scattered randomly through space like isolated grains of sand. Gravity gathers them together into groups and clusters. Small galaxies orbit larger ones. Clusters contain hundreds or thousands of galaxies bound together by gravity. And beyond those clusters are structures so enormous they barely feel real. Superclusters, the cosmic equivalent of continents. This discovery changed humanity's understanding of its place in existence yet again. Earth was not the center of the solar system. The solar system was not the center of the galaxy. The Milky Way was not the universe, and even our galaxy cluster was only part of something vastly larger. Imagine standing in a small town your entire life believing it was the whole world, only to slowly discover your town belongs to a county, then a nation, then a continent, then a planet suspended inside a giant moving web of unimaginable scale. That is essentially what astronomy has done to the human ego for the last few centuries, patiently and repeatedly. Now here is where tonight's story becomes especially fascinating. For a long time, astronomers believed our galaxy belonged to something called the Virgo Supercluster, a massive collection of galaxy groups centered around the Virgo cluster. That already sounded impressively enormous. But in 2014, scientists refined their understanding of these gigantic structures, using detailed maps of how galaxies actually move through space. And what they found revealed an even larger structure surrounding us, Laniakea. The name comes from Hawaiian and roughly translates to immense heaven or spacious sky, which feels appropriate because naming a structure containing 100,000 galaxies is probably one of those situations where understatement becomes difficult. Laniakea spans around 520 million light-years across. Just pause there for a second. 520 million light-years. The light reaching us from one side of this structure began its journey before dinosaurs existed on Earth. Back when tiny mammals still lived nervously in forests while enormous reptiles stomped around making life difficult for everything smaller than a bus. And we live inside this structure, not near it, inside it. The Milky Way drifts through one small region of Laniakea alongside neighbouring galaxies, all slowly pulled through space by gravity toward deeper concentrations of mass hidden within the cosmic web. The truly strange part is that we cannot actually see Laniakea directly the way you might see a mountain or a cloud. It does not have glowing borders. There is no giant cosmic sign reading "Welcome to Laniakea." Scientists identified it by carefully mapping the movement of galaxies, almost like tracking leaves floating along invisible currents in an ocean. Because galaxies move. Everything moves. Even on the largest scales imaginable, the universe refuses to sit still. Our galaxy and its neighbours are flowing through space towards something called the Great Attractor, an enormous gravitational region partly hidden behind the dense stars and dust of the Milky Way itself. We cannot fully observe it easily because our own galaxy blocks the view like someone standing too close to a movie screen, which feels very human somehow. Even at cosmic scales, we still struggle to see the full picture because we are stuck inside our own position. Astronomers studying galaxy motions realized that these flows revealed invisible boundaries between enormous cosmic regions. Galaxies inside Laniakea move together as part of the same gigantic gravitational system, almost like rainwater flowing through one massive drainage basin. And that comparison turns out to be surprisingly accurate. One scientist described superclusters as watersheds. Imagine rain falling across a landscape. Tiny droplets gather into streams. Streams merge into rivers. Rivers eventually flow toward common basins. In much the same way, galaxies drift through the universe along gravitational pathways shaped by dark matter and enormous concentrations of mass. The universe, on its largest scales, behaves less like scattered chaos and more like a slowly flowing ecosystem. A very large ecosystem. An ecosystem where individual galaxies are separated by millions of light years and traffic jams takes several 100 million years to develop. Which honestly makes your morning commute seem a little less stressful. Maybe. Now, one of the reasons Laniakea feels so difficult to picture is because human brains evolved for survival on African grasslands, not for understanding cosmic geography. Our ancestors needed to remember where berries grew and whether the large creature behind the bushes looked hungry. They did not need to visualize structures spanning 500 million light years. So whenever we try to imagine these distances, the brain starts substituting emotional impressions instead of true scale. We say things like vast or unimaginable, because there comes a point where numbers stop functioning properly inside ordinary thought. Even astronomers experience this. Scientists who spend their lives studying the universe still occasionally pause and quietly say things like, "Well, that's absurdly large." And Laniakea truly is absurdly large. Yet inside it, the Milky Way remains ordinary. That may actually be one of the most comforting ideas in astronomy. Our galaxy is beautiful, certainly. Spiral arms filled with stars, nebulae, black holes, planets, dust clouds, ancient star clusters, and possibly countless civilizations we have not discovered yet. But cosmically speaking, the Milky Way is fairly average. A normal galaxy and a normal region of space inside a gigantic structure among countless others. There is something calming about that. Human life often feels pressured to become extraordinary, to stand out constantly, to achieve endlessly. But the universe itself seems perfectly comfortable building beauty out of ordinary things repeated at unimaginable scales. Ordinary stars create galaxies. Ordinary galaxies create clusters. Clusters form superclusters. And somewhere inside one small spiral arm of one fairly typical galaxy, a species evolved capable of noticing all of it. That alone is remarkable. Right now, you are listening to a story told by a primate on a rocky planet orbiting a medium-sized star while drifting through a supercluster large enough to contain 100,000 galaxies. And somehow, your biggest concern earlier today may have involved replying to an email. The scale difference between daily life and cosmic reality is honestly hilarious sometimes. Still, perhaps that is what makes astronomy feel so strangely soothing late at night. It gently rearranges the importance of things. Problems do not disappear exactly, but they shrink into more manageable proportions when placed beside structures like Laniakea. The universe does not erase human life, it contextualizes it. And as astronomers slowly mapped these giant cosmic flows during the late 20th and early 21st centuries, humanity began seeing the universe differently yet again. Not as isolated galaxies floating randomly through emptiness, but as part of a colossal interconnected web shaped by gravity, dark matter, and motions unfolding over billions of years. A web so enormous that we are only beginning to understand our place inside it. Long before humans understood galaxies, superclusters, or the enormous structure called Laniakea Supercluster, the night sky looked much smaller than it does today. Not small in the literal sense, of course. Even ancient people understood that the heavens stretched far beyond mountains, oceans, and clouds. But the universe still felt enclosed somehow, like a great dome wrapped around the Earth. The stars appeared fixed in place, returning night after night with dependable precision. Constellations rose and fell with the seasons. Planets wandered slowly across the sky. The moon changed shape. The sun travelled overhead. Everything looked organised, predictable, intimate. And perhaps that is why the Milky Way fascinated people for so long. That pale glowing band stretching across dark skies looked different from ordinary stars. It was softer, hazy, almost cloud-like. Some cultures imagined it as smoke from celestial fires. Others saw rivers, pathways, or spilled milk from the gods. Ancient Greeks connected it to the goddess Hera. In Chinese mythology, it became the silver river separating two celestial lovers. Across cultures, people understood that the Milky Way was special, even if nobody knew what it truly was. To human eyes standing beneath dark skies thousands of years ago, the Milky Way felt close enough to belong to our world emotionally. It was part of the same sky that carried storms, sunlight, and seasons. Nobody imagined that this glowing band was actually composed of hundreds of billions of stars spread across distances so immense that light itself requires 100,000 years to cross it. And even after telescopes arrived, understanding came slowly. The first telescopes revealed astonishing details. Suddenly the moon had mountains. Jupiter possessed moons of its own. Venus showed phases like the moon, supporting the idea that planets orbited the sun rather than Earth. The heavens stopped looking perfect and eternal. They became physical places. Still, the Milky Way remained mysterious. Then, in 1609, Galileo Galilei pointed his telescope toward the Milky Way and made one of the most important observations in astronomical history. The cloudy band dissolved into countless faint stars. That realization changed everything quietly at first. The Milky Way was not mist or glowing vapor. It was an enormous collection of distant suns packed so densely together that human eyes blurred them into a soft river of light. Even so, nobody yet understood how enormous this structure truly was. Astronomers spent centuries trying to map the Milky Way while trapped inside it, which is a bit like attempting to map an entire forest while standing among the trees wearing foggy glasses. You can gather clues, certainly, but seeing the full structure becomes difficult when you cannot step outside it. By the 18th century, thinkers like Immanuel Kant and Thomas Wright began suggesting extraordinary possibilities. They proposed that the Milky Way might be a rotating disk of stars, and that some faint spiral-shaped objects visible through telescopes could actually be entirely separate star systems far beyond our own. These objects were called spiral nebulae. Nebula simply meant cloud, and at the time, nobody knew what they truly were. Some astronomers believed spiral nebulae were nearby clouds of gas where stars formed. Others suspected something far more dramatic: entire galaxies existing unimaginably far away. The trouble was distance. Space is difficult to measure. Difficult. Really difficult. Human beings evolved to estimate distances across fields, or perhaps from one tree to another. Astronomy demands measuring across billions of trillions of kilometers using faint points of light. It is essentially cosmic detective work performed with mathematics, patience, and occasional emotional breakdowns beside telescopes. For centuries, astronomers lacked reliable methods for measuring truly vast cosmic distances. They could observe objects clearly enough, but understanding scale remained frustratingly elusive. Then came one of the most important discoveries in astronomy: Cepheid variable stars. Now, I realise that Cepheid variable stars sounds less like a revolutionary cosmic breakthrough and more like a complicated condition your doctor apologises for explaining. But these stars became the key to unlocking the size of the universe. A Cepheid variable is a star that brightens and dims in a regular pattern. In the early 20th century, astronomer Henrietta Swan Leavitt discovered something extraordinary while studying these stars. The longer a Cepheid took to brighten and dim, the brighter it truly was. This gave astronomers an incredible tool. If you know how bright a star actually is and compare it to how bright it appears from Earth, you can calculate its distance. A nearby light looks bright, a distant light looks dim. The same principle works for stars. Leavitt's discovery became one of the foundations of modern cosmology, and yet for years she received far less recognition than she deserved, which unfortunately happened to many women in science during that era. Astronomy has always depended on brilliant minds, though history sometimes took its time admitting that properly. Using Cepheid variables, astronomers could finally begin measuring enormous distances across space with much greater confidence. Then came the famous Great Debate of 1920-19. Two astronomers, Harlow Shapley and Heber Curtis, argued publicly about the nature of the universe itself. Shapley believed the Milky Way was gigantic and contained essentially everything. Spiral nebulae existed inside our galaxy. Curtis argued the opposite. He believed spiral nebulae were separate galaxies, island universes scattered through space beyond the Milky Way. At the time, nobody knew who was correct. Imagine that for a moment. Humanity genuinely did not know whether the universe consisted of one galaxy or many. The scale of reality itself remained uncertain, and honestly, there is something wonderfully human about that. Entire civilizations built philosophies, religions, sciences and histories while not yet understanding the true size of the cosmos surrounding them. The answer finally arrived a few years later through the work of Edwin Hubble. Hubble used the enormous Hooker telescope at Mount Wilson Observatory, which at the time possessed the largest mirror in the world. During the 1920s, he carefully studied the Andromeda Spiral Nebula, searching for Cepheid variable stars, and he found them. This was monumental. By measuring those Cepheids, Hubble calculated the distance to Andromeda and discovered it lay far outside the Milky Way, much too distant to belong to our galaxy. Andromeda was another galaxy entirely, a separate island universe containing billions of stars. The Milky Way was not alone. That sentence may sound ordinary today because we grow up hearing words like galaxy constantly. But at the time, this discovery completely transformed humanity's understanding of existence. The universe became incomprehensibly larger overnight. Suddenly, the Milky Way shrank from the universe into one galaxy among many. Then astronomers discovered more galaxies, and more still, spiral galaxies, elliptical galaxies, irregular galaxies, tiny dwarf galaxies, giant galaxies containing trillions of stars. The universe expanded psychologically faster than humans could emotionally absorb it. Imagine living during that transition. 1 year, humanity occupies the entire known universe. A few years later, we are residents of one galaxy, among countless others spread across distances so vast they barely fit into thought. That must have felt deeply unsettling and exhilarating at the same time. And in many ways, astronomy has continued delivering exactly that emotional combination ever since. Once astronomers realized galaxies existed beyond the Milky Way, they immediately began asking new questions. How many galaxies are there? How far do they extend? Are they scattered randomly? Does the universe have structure? At first, galaxies appeared distributed somewhat unevenly. Some regions contained dense clusters, while others seemed sparse. But as telescopes improved and surveys expanded, patterns began emerging. Galaxies gathered together. Gravity pulled them into groups. The Milky Way itself belonged to a small collection called the Local Group, which includes Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies orbiting around larger ones. Then astronomers discovered galaxy clusters containing hundreds or thousands of galaxies bound together gravitationally. And beyond those clusters lay even larger structures. By the mid-20th century, scientists realized the universe resembled an enormous web. Galaxies stretched along filaments and walls surrounding gigantic empty regions called voids. The cosmos began looking less like scattered islands and more like a vast interconnected network, a cosmic web. That phrase sounds poetic, but it is also surprisingly accurate scientifically. On the larger scales, matter in the universe formed enormous thread-like structures shaped by gravity and dark matter over billions of years. If you could zoom impossibly far outward, the universe would not appear smooth or random. It would resemble glowing strands crossing immense darkness, and somewhere within one tiny strand sits the Milky Way. What makes this realization especially strange is how recently it happened. Human beings spent most of history unaware that galaxies even existed beyond our own. The understanding is barely a century old, 100 years. That is almost nothing historically. Your great-grandparents may have lived in a world where the Milky Way still represented the entire known universe. Now we discuss superclusters, containing hundreds of thousands of galaxies and structures stretching across hundreds of millions of light years. The scale shift is astonishing, but discovering other galaxies did more than enlarge the universe physically. It changed humanity philosophically. The Milky Way stopped feeling central. Earth had already lost its privileged cosmic position centuries earlier when heliocentrism showed planets orbit the Sun. Then the Sun became one ordinary star among billions inside the Milky Way. Then the Milky Way itself became one galaxy among countless others. Each discovery pushed humanity farther from the imagined center of creation. Yet strangely, many people found comfort in that rather than despair. Because there is another way to interpret cosmic scale, not as evidence of insignificance but as evidence of connection. The atoms inside your body were forged inside ancient stars. The oxygen you breathe, the calcium in your bones, the iron in your blood, all emerged from stellar furnaces billions of years ago. Human beings are not separate from the cosmos observing it from afar. We are part of it. The universe became conscious enough to study itself through us. That idea may sound dramatic late at night, but scientifically speaking, it is true in a very literal sense. And once galaxies entered human awareness, curiosity accelerated rapidly. Astronomers began cataloguing them obsessively. Spiral galaxies rotated elegantly through space. Elliptical galaxies drifted like enormous glowing eggs. Some collided, some merged, some produced furious bursts of star formation while others became quiet and ancient. Entire cosmic ecosystems emerged. Then another astonishing discovery arrived. The universe itself was expanding. Hubble noticed that distant galaxies moved away from us, and the farther they were, the faster they receded. Space itself stretched between galaxies like rising dough, carrying raisins apart. This became one of the foundational discoveries of modern cosmology. The universe was not static, it evolved, which meant that if you rewound cosmic history backward far enough, everything must once have been closer together. Eventually, this realization led toward the idea of the Big Bang. Suddenly, galaxies were not eternal fixtures in static space. They were participants in an evolving universe born billions of years ago, and still the discoveries kept coming. Clusters gathered into superclusters. Superclusters formed filaments. Dark matter shaped invisible gravitational scaffolding. Gigantic flows of galaxies drifted toward mysterious regions of concentrated mass. Eventually, astronomers would identify structures like Laniakea supercluster, revealing that even galaxy clusters belong to larger gravitational systems. But all of that depended on one crucial realization first. The Milky Way was not alone. That single discovery opened the door to modern cosmology. Without it, there would be no understanding of superclusters, cosmic webs, or giant structures stretching across hundreds of millions of light years. Humanity first had to accept that the faint spiral smudges in old telescopes were not nearby clouds, but entire galaxies filled with stars, planets, and perhaps civilizations of their own. Once astronomers understood galaxies existed everywhere, the next mystery became impossible to ignore. Why did they gather together the way they did? At first glance, the universe looks scattered. Stars appear sprinkled randomly across the night sky. Galaxies photographed through telescopes seem tossed carelessly through darkness, like glowing grains of sand. Even modern images of deep space can give the impression of cosmic loneliness, isolated islands drifting through endless emptiness with unimaginably vast distances between them. But appearances can be deceptive, because the universe, despite all its chaos and violence, has a remarkable tendency to organize itself. Not perfectly, not neatly, but persistently. And once astronomers realized the Milky Way was only one galaxy among many, they began noticing something peculiar. Galaxies were not distributed evenly through space. They clustered together, they gathered, they formed neighborhoods. In some regions of the cosmos, galaxies appeared packed densely together, swirling around one another inside enormous gravitational communities. Elsewhere, space stretched almost empty for hundreds of millions of light years. The universe, it turned out, resembled less a random spray of objects and more a giant network of cosmic cities separated by vast dark countryside. That realization slowly changed how scientists viewed the large-scale structure of reality itself. The first clues emerged during the early 20th century as astronomers catalogued more and more galaxies. With better telescopes came better surveys, and with better surveys came patterns. Certain galaxies consistently appeared near others. Large elliptical galaxies often sat near the centres of clusters surrounded by smaller companions. Spiral galaxies grouped together. Some clusters contained hundreds of galaxies. Others contained thousands. Gravity was clearly shaping something enormous. Now, gravity is an odd force when viewed on cosmic scales. Here on Earth, gravity feels relatively weak. You can defeat the gravity of the entire planet simply by standing up from a chair, though admittedly some mornings require more emotional effort than physics. But gravity possesses one very important characteristic. It only attracts. There is no negative gravity pushing things apart locally in the way magnets can repel each other. Gravity gathers matter together relentlessly over time. Tiny imbalances grow larger. Slightly denser regions attract more material, becoming denser still. And given billions of years, gravity becomes astonishingly good at building structure. The early universe after the Big Bang was surprisingly smooth overall. Matter spread through space almost evenly, but not perfectly evenly. Tiny fluctuations existed, slight regions where matter density was a little higher than average. Those tiny imperfections changed everything. Over immense stretches of time, gravity amplified them. Denser regions attracted surrounding gas and dark matter. Small clumps grew larger. Larger clumps merged into enormous structures. Stars formed. Galaxies emerged. Galaxies gathered into groups. Groups formed clusters. Eventually, the universe developed a kind of cosmic architecture. Not designed architecture, of course. Nobody laid out blueprints for galaxies. But natural processes created patterns anyway, much the way rivers carve branching networks across landscapes without consulting engineers beforehand. One of the most fascinating aspects of galaxy formation is how social galaxies appear to be. That may sound ridiculous since galaxies are giant rotating collections of stars rather than conscious beings organising dinner parties. But astronomically speaking, isolation is surprisingly uncommon. Most galaxies belong to groups or clusters. The Milky Way itself belongs to the local group, which contains more than 50 known galaxies. Most are small dwarf galaxies orbiting large ones like the Milky Way or Andromeda galaxy. Andromeda itself is enormous, roughly similar in size to the Milky Way and currently moving toward us at around 110 kilometers per second, which sounds alarming at first. Fortunately, space is very large. The collision will not happen for about 4.5 billion years, meaning you're probably safe postponing concerns about it until after tomorrow's responsibilities are handled. Still, galaxy collisions are common throughout the universe. In fact, galaxies grow partly by merging together over time. Astronomers observing distant space regularly see galaxies interacting gravitationally, stretching one another into strange distorted shapes through tidal forces. Some collisions trigger furious waves of star formation. Gas clouds compress. New stars ignite by the billions. Entire galaxies briefly become brilliant cosmic fireworks displays before eventually settling into calmer forms. Others merge slowly and quietly over hundreds of millions of years like sleepy cosmic traffic accidents unfolding in extreme slow motion. The Milky Way itself contains evidence of past mergers. Streams of stars arc around our galaxy, remnants of smaller galaxies consumed long ago. Even now, the Milky Way continues pulling in dwarf galaxies through gravity. The universe recycles constantly. Nothing remains entirely separate forever. As astronomers studied larger galaxy collections during the 20th century, they discovered structures of astonishing scale. Galaxy clusters became some of the most impressive objects in the universe. Take the Virgo cluster, for example. It contains roughly 1,300 to 2,000 galaxies packed into a region about 15 million light-years across. Giant elliptical galaxies dominate its centre, including the enormous galaxy M87, which houses one of the most massive black holes ever observed. That black hole gained particular fame in 2019 when astronomers captured the first direct image of a black hole's shadow using the Event Horizon Telescope, which remains one of the most extraordinary scientific photographs humanity has ever produced. Not because it is visually dramatic exactly, though it certainly is, but because it represents human beings successfully imaging an object so extreme that not even light escapes from it. A species of upright primates on a small planet managed to photograph the edge of space-time distortion in another galaxy. Honestly, that is impressive enough to excuse a great many human shortcomings. Now, galaxy clusters do not merely contain galaxies. They also contain enormous amounts of hot gas filling the spaces between galaxies themselves. This gas becomes so hot, tens of millions of degrees, that it glows in X-rays. In fact, much of the ordinary matter inside clusters exists not in stars but in this thin, superheated plasma spread between galaxies. And then there is dark matter. Dark matter appears everywhere in cosmic structure formation. Galaxies rotate too quickly to remain stable based solely on visible matter. Clusters contain far more gravitational pull than observable stars and gas can explain. Something invisible contributes additional mass. Scientists call it dark matter, not because it is evil or especially dramatic, though admittedly the name does sound suspiciously like a rejected comic book villain, but because it neither emits nor reflects light. We cannot see dark matter directly. We infer its existence through gravity, and without dark matter, galaxies and clusters would not form the way they do. Current cosmological models suggest dark matter acts like invisible scaffolding underlying the cosmic web. Ordinary matter falls into dark matter structures gravitationally, eventually forming galaxies and clusters along those hidden frameworks. So in a sense, the visible universe may simply illuminate a much larger invisible structure beneath it, which is a wonderfully unsettling thought late at night. Now, one reason galaxy clusters fascinate astronomers so deeply is because they reveal the universe behaving almost like biology or sociology on gigantic scales. Galaxies influence one another constantly. A galaxy moving through a dense cluster experiences gravitational interactions with neighbours. Gas can be stripped away, shapes become distorted, star formation changes. Some galaxies age rapidly inside crowded environments, while others remain active and vibrant. Environment matters cosmically just as it does biologically. Galaxies living inside dense clusters often become older, redder, and quieter. Their star formation slows as available gas disappears. Meanwhile, galaxies in less crowded regions continue forming bright young stars for longer periods. The universe develops ecosystems, and the scale of those ecosystems kept growing larger as astronomers mapped more of space. During the late 20th century, galaxy surveys exploded in size and sophistication. Massive observational projects began charting the positions of hundreds of thousands of galaxies across enormous regions of the cosmos. One famous survey, the Sloan Digital Sky Survey, helped reveal the universe's large-scale structure in breathtaking detail. What emerged shocked even experienced astronomers. Galaxies and clusters arranged themselves into enormous filaments stretching across hundreds of millions of light years. These filaments connected dense nodes filled with galaxy clusters while surrounding gigantic empty voids. The universe resembled foam, or neural networks, or perhaps an unimaginably vast spiderweb suspended through darkness. Human beings immediately began comparing the cosmic web to familiar structures because the patterns looked strangely organic. Some maps even resembled microscopic brain tissue, despite the scales differing beyond comprehension. Of course, these similarities are mostly visual coincidence rather than evidence of some mystical connection between brains and the cosmos. Still, it says something interesting about nature, that similar structural patterns emerge repeatedly across wildly different scales. Gravity, flow dynamics, and network formation often create branching systems, whether you're looking at river basins, fungal growth, neurons, blood vessels, or galaxies. Nature enjoys patterns. Now, perhaps the most emotionally strange aspect of the cosmic web is the enormous emptiness between structures. Space is mostly nothing, not metaphorically, literally. If galaxies are cities, then the spaces between them are unimaginably empty wildernesses. Even inside galaxy clusters, individual galaxies remain separated by millions of light years, and yet gravity still binds them together. That fact alone reveals gravity's incredible patience. Gravity does not rush. It operates over immense timescales impossible for human intuition to grasp comfortably. Galaxy clusters evolve over billions of years. Superclusters form gradually through cosmic flows so slow that entire civilizations rise and disappear before noticeable changes occur. Human life unfolds inside a universe moving with almost geological calm on its larger scales. And perhaps that calmness contributes to why astronomy feels soothing for so many people. The cosmos does not hurry. Stars burn for billions of years. Galaxies drift slowly through darkness. Superclusters evolve patiently across epochs longer than human history could ever fully contain. The universe is ancient enough that urgency starts feeling slightly unnecessary, not meaningless exactly, just smaller. Meanwhile, here on Earth, human beings continue worrying about emails while drifting through this gigantic cosmic network completely unnoticed. Right now, the Milky Way moves through space surrounded by neighbouring galaxies, all participating in flows shaped by gravity across the enormous structure of Laniakea Supercluster. And for a long time, astronomers struggled to understand exactly where our galaxy fit inside that larger structure. Because once galaxies formed clusters, and clusters gathered into even bigger arrangements, the next question became unavoidable. What neighbourhood does the Milky Way actually belong to? Compared to the gigantic scale of Laniakea Supercluster, the place we actually live is surprisingly small. Cosmically speaking, our immediate neighbourhood is less a sprawling empire and more a quiet rural town tucked somewhere deep inside an enormous continent of galaxies. Astronomers call this neighbourhood the local group, a modest collection of galaxies bound together by gravity and drifting through space as a kind of extended cosmic family. And like many families, It contains a few dominant personalities, numerous smaller relatives, occasional collisions, and enough gravitational drama to keep astronomers occupied for decades. The local group spans roughly 10 million light-years across and contains more than 50 known galaxies, though the exact number keeps changing as astronomers discover new dwarf galaxies hiding in the darkness around larger ones. Most of these galaxies are tiny, really tiny by galactic standards. Some contain only a few million stars, which may sound impressive until you remember the Milky Way contains somewhere between 100 and 400 billion stars. Scale in astronomy is wonderfully unfair sometimes. The local group is dominated by three large spiral galaxies: the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. Around these larger galaxies orbit swarms of dwarf galaxies like cosmic moons trapped inside giant gravitational systems. If you could somehow step impossibly far outside the local group and look back at it from millions of light-years away, it would not appear especially impressive compared to giant galaxy clusters elsewhere in the universe. No enormous central cluster dominates our region. No massive elliptical supergiants overwhelm everything nearby. Instead, the local group feels relatively calm, sparse, a bit suburban by cosmic standards, and perhaps that is fortunate. Dense galaxy clusters can become violent places. Galaxies collide frequently. Hot gas floods the space between galaxies. Supermassive black holes erupt with intense radiation. Gravitational interactions constantly distort galactic shapes. The local group is quieter. Not peaceful exactly, because the universe never fully commits to peace, but calmer. The Milky Way itself is a barred spiral galaxy, meaning it possesses a central elongated structure of stars extending through its core. Spiral arms curve outward from that bar like enormous glowing rivers filled with stars, gas clouds, nebulae, and dark dust lanes. Somewhere inside one of those minor spiral arms sits our solar system. Not near the centre, not at the edge, just somewhere in the middle regions orbiting quietly around the galactic core. And that orbit takes time, a great deal of time. The solar system circles the centre of the Milky Way at around 828,000 kilometers per hour, yet one complete orbit still requires roughly 225 to 250 million years. Dinosaurs lived during a different galactic year than we do now. That thought never really becomes normal no matter how many times you hear it. Meanwhile, beyond the Milky Way's glowing disk lies the Andromeda Galaxy, our largest galactic neighbour and eventual collision partner. Andromeda sits about 2.5 million light-years away. On dark nights in places free from light pollution, human eyes can actually see it without telescopes as a faint fuzzy patch in the sky. That tiny blur contains roughly 1 trillion stars. Again, astronomy enjoys giving the human brain impossible assignments. What makes Andromeda especially important is its motion relative to us. Most galaxies in the expanding universe move away from one another as space stretches over time. Yet Andromeda is moving toward the Milky Way because the gravitational attraction between our galaxies overcomes local cosmic expansion. At some point roughly 4 to 5 billion years from now, the two galaxies will begin merging. Now, when people hear galaxy collision, they often imagine catastrophic stars smashing together like cosmic billiard balls exploding across space. In reality, galaxy mergers are strangely gentle considering their scale. Stars almost never collide directly because galaxies are mostly empty space. If the Sun were the size of a grain of sand, the nearest star would still sit kilometers away. Galactic collisions involve gravity rearranging enormous stellar systems, gradually over immense periods. Still, the visual results would be spectacular. As the Milky Way and Andromeda approach each other, both galaxies would distort gravitationally. Spiral arms would stretch, gas clouds would compress. New waves of star formation would ignite across both systems. The night sky from Earth, assuming Earth still exists and assuming future beings are around to watch, would become extraordinary. Andromeda would grow larger over millions of years until it dominated huge portions of the sky. Eventually the galaxies would merge into one enormous elliptical galaxy, sometimes nicknamed Milkomeda, which sounds slightly less like an elegant astronomical term and more like a breakfast drink marketed toward exhausted graduate students. Still, the merger represents a natural stage in galactic evolution. Galaxies grow partly through consumption and combination. The Milky Way itself bears evidence of many smaller mergers throughout its history. In fact, astronomers continue discovering remnants of ancient galaxies absorbed long ago. One particularly fascinating example is the Sagittarius dwarf spheroidal galaxy, a small galaxy currently being torn apart and absorbed by the Milky Way's gravity. Streams of its stars wrap around our galaxy like faint stellar ribbons. The Milky Way is actively eating smaller galaxies even now, quietly, patiently. Cosmically speaking, our galaxy is less a stable island and more a constantly evolving ecosystem shaped by billions of years of interactions. Around both the Milky Way and Andromeda orbit numerous dwarf galaxies. These tiny companions come in several varieties. Some are irregular galaxies containing scattered young stars and gas clouds. Others are dwarf spheroidals, faint ancient systems with little ongoing star formation. Many contain surprisingly large amounts of dark matter compared to ordinary visible matter. Dark matter appears especially important in dwarf galaxies because their visible stars alone cannot explain how strongly gravity holds them together. Without dark matter, many dwarf galaxies should simply fly apart, and yet they remain intact, which means most of the local group may actually consist of invisible mass-shaping motions we only partly understand. That idea becomes stranger the longer you think about it. The galaxies visible through telescopes may represent only a fraction of the true gravitational landscape surrounding us. Invisible structures guide everything. Now, one reason astronomers study the local group so intensely is because it offers a nearby laboratory for understanding galaxy evolution. Distant galaxies appear small and faint even through powerful telescopes, but galaxies inside the local group can be studied in extraordinary detail. Astronomers can resolve individual stars inside neighbouring galaxies. They can map star formation histories, chemical compositions, dark matter distributions, and gravitational interactions with remarkable precision. In a sense, the local group became humanity's galactic classroom, and what we learned there reshaped our understanding of the broader universe. For example, astronomers once believed galaxies formed quickly and remained relatively unchanged afterward. But observations of local group galaxies revealed far more dynamic histories. Galaxies merge, evolve, consume neighbours, lose gas, form new stars, and transform over time. The universe is active, constantly changing. Even structures that appear eternal from human perspectives evolve gradually across cosmic timescales. One particularly interesting aspect of the local group involves its future, not just the Milky Way-Andromeda collision, but the long-term isolation that awaits. Right now, the universe continues expanding due to dark energy, the mysterious force accelerating cosmic expansion. Over billions upon billions of years, distant galaxies beyond the local group will eventually move away faster than light can bridge the expanding space between us. Future astronomers living trillions of years from now may see only the merged remnant of the local group surrounded by darkness. Most galaxies will disappear beyond the observable horizon. The cosmic web itself will slowly fade from view, which means humanity happens to exist during a very fortunate era cosmologically. We live at a time when the universe still reveals its large-scale structure clearly enough for discovery. That timing feels oddly generous. Of course, the local group itself continues moving through much larger cosmic structures even now. Our entire galactic neighbourhood drifts toward the Virgo cluster as part of larger gravitational flows inside Laniakea Supercluster. The Milky Way is not stationary, neither is the local group. Everything moves. Sometimes it helps to pause and appreciate how strange ordinary life truly is within this context. At this very moment, you are sitting on a rotating planet orbiting a star inside a galaxy travelling through space alongside dozens of neighbouring galaxies, all drifting through a supercluster hundreds of millions of light years wide. And despite all that motion, your coffee can still spill because you move too quickly reaching for it. Human experience remains wonderfully local, even inside cosmic enormity. Although the local group feels large from our perspective, it represents only a tiny piece of a much larger galactic arrangement. Far beyond the quiet familiarity of the local group lies something much larger, something heavier, something powerful enough to tug on entire galaxies across tens of millions of light years, the Virgo Cluster. If the local group is a small town drifting through cosmic countryside, then the Virgo Cluster is a gigantic crowded city glowing in the distance, packed with galaxies, hot gas, dark matter and gravitational influence strong enough to shape the motions of everything nearby, including us. And the truly strange part is that even though this enormous structure contains thousands of galaxies and stretches across millions of light years, human beings can actually observe part of it with amateur telescopes from Earth. Not easily, of course. The Virgo Cluster lies about 55 million light-years away in the direction of the constellation Virgo. To the naked eye, it remains invisible for most people unless skies are exceptionally dark and clear. But through telescopes, the region becomes crowded with faint glowing smudges. Each smudge is an entire galaxy. That realization never fully loses its power. A faint blur through glass becomes a structure containing hundreds of billions of stars. Astronomy repeatedly turns tiny points of light into impossible realities. The Virgo Cluster is the nearest major galaxy cluster to the Milky Way, which makes it enormously important scientifically. Because it is relatively close by cosmic standards, astronomers can study it in tremendous detail, and what they found there helped reveal how galaxies behave inside dense environments. The cluster contains somewhere between 1,300 and 2,000 galaxies, depending on how membership gets defined. Some are giant ellipticals, others are spirals. Many are dwarf galaxies swarming through the cluster's gravitational field, like tiny fish around larger creatures. At the centre of the Virgo cluster sits one of the largest galaxies in the nearby universe, Messier 87, often shortened to M87. M87 is absurdly massive. It contains trillions of stars and spans roughly 1 million light-years across, making it far larger than the Milky Way. At its core lies a supermassive black hole weighing billions of times more than our Sun. And this black hole became historically famous in 2019 when astronomers from the Event Horizon telescope released the first direct image of a black hole's shadow. That glowing orange ring appeared on news broadcasts around the world. For many people, it felt almost unreal. Humanity had somehow photographed the edge of a black hole 55 million light-years away. To achieve that image, scientists effectively transformed Earth itself into a giant telescope by linking radio observatories across the planet. Massive amounts of data were combined using atomic clocks precise enough to detect tiny timing differences between observatories separated by continents. All of that effort just to glimpse the shadow of something invisible, and the target happened to sit inside the Virgo cluster. Now, one reason galaxy clusters become so massive is because gravity never really stops working. Over billions of years, smaller groups and galaxies fall inward toward dense regions, building larger and larger structures. The Virgo cluster grew this way gradually, gathering galaxies through cosmic time like a snowball rolling downhill, gathering more snow. Except the snowflakes are galaxies, and the hill is curved space-time, which admittedly makes winter sports sound considerably more intimidating. Inside the Virgo cluster, galaxies move rapidly around one another under the influence of immense gravitational forces. Some race through the cluster at thousands of kilometers per second. The entire region behaves less like a static collection of objects and more like a gigantic gravitational ecosystem in constant motion. and the environment inside that ecosystem can become harsh. Galaxies entering dense clusters often change dramatically over time. Spiral galaxies rich in gas may lose that gas through interactions with hot plasma filling the cluster. Star formation slows. Shapes become distorted. Some galaxies merge. Others are stretched gravitationally into strange elongated forms. The cluster environment transforms galaxies. Astronomers sometimes compare galaxy clusters to crowded cities because dense environments influence behavior so strongly. In isolated regions, galaxies evolve relatively quietly. Inside clusters, constant interactions reshape them continuously. And the Virgo cluster is busy, very busy. Beyond the galaxies themselves, the cluster contains enormous amounts of extremely hot gas spread between galaxies. This gas reaches temperatures of tens of millions of degrees and glows brightly in X-rays. If human eyes could see X-rays naturally, the Virgo cluster would look completely different from the calm, starry skies we know. Vast, glowing clouds would fill the spaces between galaxies, revealing violent energetic processes unfolding continuously across millions of light years. Space, despite appearances, is not empty. Even the regions between galaxies contain matter, radiation, magnetic fields, and invisible dark matter structures shaping everything through gravity. Dark matter becomes especially important in clusters because visible galaxies alone cannot explain the amount of gravity observed. Galaxies inside the Virgo cluster move too quickly to remain gravitationally bound unless enormous amounts of unseen mass exist. Once again, the universe hints that most of reality remains invisible to us directly. Current estimates suggest ordinary matter, stars, gas, planets, dust, and everything humans can physically touch, makes up only about 5% of the universe. The rest consists mostly of dark matter and dark energy. Which means the familiar visible universe may represent only a thin glowing surface layer over something vastly larger and stranger. That realization can feel unsettling initially, or oddly comforting, sometimes both simultaneously. Now the Virgo cluster matters deeply to our story because the local group itself moves toward it. Not directly into it exactly, but generally toward the larger gravitational region surrounding Virgo. For decades, astronomers noticed something peculiar while studying galactic motions nearby. Galaxies did not simply move outward uniformly due to cosmic expansion. Many also possessed additional motions, pulling them toward dense concentrations of mass. The local group participates in one of these flows. Our entire galactic neighborhood drifts through space at roughly 600 kilometers per second, relative to the cosmic microwave background radiation, the faint afterglow left from the early universe. That motion points roughly toward the region containing the Virgo cluster and beyond. So although Earth feels stationary beneath our feet, we are actually participating in gigantic cosmic migration patterns shaped by gravity on scales almost impossible to visualize properly. The Milky Way moves. The local group moves. The Virgo cluster moves. Even entire superclusters move. The universe is restless at every scale. This understanding emerged gradually during the 20th century as astronomers improved methods for measuring galactic distances and velocities. Once scientists could determine both where galaxies were and how they moved, large-scale patterns began appearing. Galaxies flowed toward dense regions, like rivers draining toward lower elevations. This analogy became increasingly important because cosmic structure behaves surprisingly like geography. Matter gathers into valleys of gravity. Galaxies stream along filaments toward massive nodes. Enormous empty voids separate denser structures like vast cosmic deserts. And somewhere inside these enormous flows sits the Virgo cluster, acting as one of the major gravitational centers in our region of the universe. For a long time, astronomers believed the Virgo cluster defined the center of our local supercluster entirely. The larger galactic structure containing the Milky Way became known simply as the Virgo Supercluster. That seemed reasonable based on available observations, but science has a habit of enlarging reality every time humans become comfortable with their current understanding. By the early 21st century, astronomers had already learned something humbling about the universe. Every time humanity thought it understood the largest structures in existence, the cosmos quietly revealed something even bigger. First came planets, then galaxies, then galaxy clusters, then superclusters, and eventually scientists realized that even superclusters were not isolated objects floating neatly through space. They belonged to something larger still, an enormous interconnected system shaped by gravity across distances so vast that ordinary language begins struggling to cooperate. That realization would eventually lead to the discovery of Laniakea Supercluster, a structure so immense that the Milky Way becomes almost impossible to notice inside it. And perhaps the strangest part of this discovery is that nobody actually saw Laniakea directly at first. Astronomers mapped it almost the way ancient sailors mapped invisible ocean currents, by watching movement. To understand how this happened, we first need to pause for a moment and consider something surprisingly difficult. How do you map the universe when you are trapped inside it? That problem has haunted astronomy for centuries. Human beings cannot step outside the cosmos and photograph it from afar. We cannot rise above the Milky Way for a better angle. Everything we know about large-scale cosmic structure must be inferred from tiny amounts of light reaching Earth, after journeys lasting millions or billions of years. Astronomy is less like sightseeing and more like reconstruction. Scientists gather clues, patterns, motions, spectra, distances, and slowly, carefully, they piece together a picture large enough for the human mind to barely tolerate. Now, by the late 20th century, astronomers had already mapped many nearby galaxies and clusters. They knew the Milky Way belonged to the local group. They knew the local group drifted toward the Virgo cluster. They also understood that galaxies formed enormous filaments and walls across the universe, but something still felt incomplete. Because galaxy motions did not entirely match expectations, the universe itself expands. Ever since Edwin Hubble discovered galactic redshifts during the 1920s, astronomers understood that distant galaxies generally move away from one another as space stretches over time. This expansion behaves somewhat like raisins separating inside rising bread dough. The farther apart galaxies are, the faster they usually recede from each other. That is the large-scale trend. But individual galaxies also possess local motions caused by gravity. Astronomers call these peculiar velocities, which sounds wonderfully dramatic considering it essentially means movement that does not follow the average expansion. And when scientists measured these peculiar velocities carefully, they noticed something important. Galaxies in our region of the universe appeared flowing together. Not randomly, not chaotically, together. Entire groups and clusters drifted towards shared gravitational destinations. Something enormous shaped those motions. At first, astronomers focused heavily on the region around the Virgo cluster, because nearby galaxies clearly showed gravitational attraction toward it. This led scientists to define the larger surrounding structure as the Virgo Supercluster. That framework worked reasonably well for decades, but eventually the data improved, and better data has a habit of ruining comfortable ideas. During the late 20th century and early 21st century, astronomers developed increasingly sophisticated methods for measuring galaxy distances and motions across huge portions of space. One major challenge involved separating ordinary cosmic expansion from local gravitational movement. Imagine standing beside a wide-flowing river while small fish swim through the current. If you only observe their motion casually, it becomes difficult to tell whether the fish move independently or simply drift with the river itself. Galaxies behave similarly. The expansion of the universe carries galaxies apart generally, but gravity creates local flows superimposed on top of that expansion. To map true large-scale structures, astronomers needed to identify those flows, and this required immense amounts of data. Scientists gathered observations from thousands of galaxies, measuring both their distances and velocities. They studied how galaxies deviated from expected cosmic expansion patterns. Slowly, hidden structures began emerging from the data almost like invisible landscapes revealed by water movement. One of the key figures in this work was Brent Tully, whose research helped redefine humanity's understanding of our cosmic neighbourhood. Tully and his collaborators approached the problem differently from earlier astronomers. Instead of defining superclusters simply by where galaxies appeared concentrated visually, they focused on how galaxies actually moved. This changed everything. Because gravity leaves fingerprints on motion. Galaxies falling toward the same gravitational basin belong to the same larger structure, much the way streams flowing toward the same ocean belong to the same watershed. That watershed analogy became central to the discovery of Laniakea. Imagine rain falling across mountains and valleys. Tiny streams form first. Streams merge into rivers. Rivers flow toward common basins determined by the landscape beneath them. Now replace water with galaxies, replace valleys with gravitational wells, and replace landscapes with invisible dark matter structures stretching across hundreds of millions of light years. The universe behaves remarkably similarly. Galaxies drift through enormous gravitational flow patterns shaped by matter distributed across cosmic scales. By tracing those motions, astronomers realized our region of the universe formed one gigantic interconnected basin, Laniakea. The name was chosen deliberately and beautifully. It comes from Hawaiian words meaning immense heaven or spacious sky, which feels fitting because discovering Laniakea expanded humanity's mental map of existence yet again. Officially described in 2014, Laniakea spans roughly 520 million light-years across and contains approximately 100,000 galaxies. 100,000? Just pause there for a second. The Milky Way contains hundreds of billions of stars. Laniakea contains around 100,000 entire galaxies, and somewhere inside one ordinary spiral arm of one ordinary galaxy sits Earth. There is something wonderfully calming about how thoroughly the universe ignores human ego. Now, one of the reasons Laniakea feels difficult to picture is because superclusters do not possess sharp physical edges like planets or stars. You cannot point to a glowing boundary in space and say, "There, Laniakea ends exactly there." Instead, its boundaries are defined by motion. Galaxies inside Laniakea flow toward shared gravitational attractors. Galaxies outside flow elsewhere. This means Laniakea is less an object and more a dynamic region shaped by gravitational behavior, almost like a weather system or an ocean current. In fact, astronomers created visualizations of these galactic flows that look astonishingly fluid. Streams of galaxies curve through space along invisible pathways, converging toward dense regions of mass hidden deep inside the cosmic web. Watching these maps feels strangely hypnotic. The universe starts looking alive. Not alive biologically, of course. Galaxies are not conscious rivers. But large-scale cosmic motion possesses an organic quality difficult to ignore. Matter flows, structures merge, gravity sculpts patterns over billions of years, the cosmos evolves, and all of it happens incredibly slowly. That slowness matters because human intuition struggles badly with cosmic timescales. Continents drifting across Earth already feel difficult to notice directly, because geological time unfolds far beyond individual lifetimes. Cosmic structures evolve even more gradually. Laniakea itself is not static. Galaxies continue moving through it constantly. Clusters interact. Gravity reshapes flows. Over immense spans of time, the structure itself changes. And yet from human perspectives, it appears eternal simply because our lives are tiny compared to cosmic evolution. One fascinating aspect of the Laniakea discovery involved visualizing something called the Great Attractor. Now, the Great Attractor sounds less like a scientific term and more like a villain from an expensive science fiction film, but it refers to a very real gravitational region influencing the motions of galaxies across enormous distances. For decades, astronomers noticed that the Milky Way and neighbouring galaxies drifted toward a particular region of space faster than expected. Something massive lurked there. The problem was location. The Great Attractor lies partly behind the dense plain of the Milky Way itself, in a region astronomers sometimes call the zone of avoidance, because dust and stars block direct observation, which feels oddly relatable. Even on cosmic scales, our own position limits what we can see clearly. Still, improved observations eventually revealed enormous galaxy concentrations hidden beyond the Milky Way, including structures like the Supercluster. The Great Attractor itself may not be one single object exactly, but rather part of a broader gravitational landscape involving multiple massive structures tugging on galaxies throughout our region of the universe. And all of these flows help define Laniakea. One especially remarkable thing about the discovery is how modern it is. Humanity has known about galaxies beyond the Milky Way for barely a century. Laniakea itself entered scientific literature only recently in historical terms. There are people alive today who spent childhoods learning one version of the universe and adulthoods learning another. That constant expansion of understanding is one of astronomy's defining characteristics. The universe repeatedly turns out larger, more interconnected, and more complicated than expected, and yet somehow also more beautiful. Now, not every astronomer defines superclusters exactly the same way. Cosmic structures become tricky because gravity competes against the expansion of the universe itself. Some scientists argue that superclusters like Laniakea are not gravitationally bound enough to remain intact permanently. Eventually, cosmic expansion may pull parts of these structures apart over unimaginable timescales. In other words, Laniakea may not represent a stable, eternal object. It may be more like a temporary arrangement inside a constantly evolving universe, which again feels strangely human. Even the largest known structures are not permanent. Still, the discovery fundamentally changed how humanity visualizes its place in the cosmos. Before Laniakea, many people imagined galaxies and clusters as relatively isolated objects. Afterward, the universe looked more like an enormous interconnected flow system. The Milky Way stopped being merely a galaxy. It became part of a river of galaxies moving through gigantic invisible landscapes shaped by gravity and dark matter. And perhaps that is the most fascinating emotional shift astronomy keeps producing. Every discovery makes humanity simultaneously smaller and more connected. Smaller because we occupy only a tiny portion of reality. More connected because we increasingly realize nothing exists in true isolation. Earth belongs to the solar system. The solar system belongs to the Milky Way. The Milky Way belongs to the local group. The local group belongs to Laniakea. And Laniakea itself belongs to the cosmic web stretching across the observable universe. A chain of structures nested inside structures almost beyond comprehension. Right now, as you sit listening quietly somewhere on Earth, you are participating in these motions whether you notice them or not. The Earth rotates. The Earth orbits the Sun. The solar system circles the Milky Way. The Milky Way drifts with the local group. The local group flows through Laniakea, and Laniakea itself moves through the evolving universe. All while daily life continues normally. People answer emails, wash dishes, miss buses, fall asleep on couches. The contrast between cosmic scale and ordinary existence never stops being slightly funny. Still, mapping Laniakea revealed something deeply important about the universe. Galaxies do not merely exist beside one another. They flow together through gigantic gravitational landscapes. And once astronomers understood that, the next question became unavoidable. What exactly is a supercluster in the first place? By the time astronomers identified Laniakea supercluster, Humanity had already become somewhat emotionally numb to large numbers, which is understandable. Astronomy has a habit of escalating scale so aggressively that eventually the brain begins reacting to phrases like 500 million light years, the same way it reacts to complicated terms in legal documents. You recognize the words individually, you simply stop believing them collectively. Still, the idea of a supercluster deserves a proper slow explanation because these structures represent some of the largest patterns ever discovered in the universe. And strangely enough, they are not quite what many people imagine. When most of us hear the word cluster, we instinctively picture something tightly packed together. Grapes on a stem, bees in a swarm, maybe students gathered around free pizza at university events. But cosmic structures behave differently because space itself is unbelievably enormous. A galaxy cluster, for example, can contain thousands of galaxies while still remaining mostly empty space. Individual galaxies inside clusters are often separated by millions of light years, and superclusters become larger still, much larger. A supercluster is essentially a gigantic region of the universe where multiple galaxy groups and galaxy clusters gather together into enormous interconnected structures shaped by gravity. But unlike smaller galaxy clusters, superclusters are not always tightly gravitationally bound systems. That distinction matters. The universe itself expands continuously. Space stretches over time, carrying distant galaxies apart. On smaller scales, gravity can overcome this expansion and hold structures together. Planets remain bound to stars. Stars remain bound inside galaxies. Galaxies remain bound inside clusters. But on the larger scales, cosmic expansion becomes increasingly powerful. This means superclusters exist in a strange middle category. They are real structures. Galaxies inside them clearly share large-scale flows and relationships. Yet parts of some superclusters may eventually drift apart over cosmic timescales due to the expansion of the universe. In other words, superclusters are not solid objects. They are more like enormous patterns. Patterns shaped by gravity, dark matter, and the evolving geometry of space itself. Now, to understand how gigantic superclusters truly are, it helps to build upward gradually from smaller cosmic structures. Let us begin close to home. The Earth orbits the Sun. The Sun belongs to the Milky Way. The Milky Way belongs to the Local Group. The Local Group belongs to Laniakea Supercluster, and Laniakea itself belongs to the Cosmic Web, the largest known structure in the observable universe. Each step upward increases scale dramatically. The solar system already feels enormous from human perspectives. Neptune orbits roughly 4.5 billion kilometers from the Sun. Light itself requires hours to cross the outer solar system. Then the Milky Way expands that scale into absurdity. 100,000 light-years wide, hundreds of billions of stars. Then the Local Group extends across roughly 10 million light-years, and Laniakea stretches around 520 million light-years across. At that point, ordinary human intuition quietly leaves the room. One useful way to think about superclusters is through geography. Imagine Earth viewed from high above. Cities gather into metropolitan regions. Metropolitan regions connect into larger economic corridors. Roads, rivers, trade routes, and geography influence how populations cluster together. The universe behaves similarly on enormous scales. Galaxies gather into groups, groups gather into clusters, clusters connect through filaments into superclusters. And surrounding everything are enormous cosmic voids where relatively few galaxies exist at all. This creates the cosmic web, one of the most astonishing discoveries in modern astronomy. Now, the cosmic web itself emerged from tiny fluctuations in the early universe, after the Big Bang. The young universe was surprisingly smooth overall, but not perfectly smooth. Slightly denser regions contained a little more matter than average. Gravity amplified those tiny differences over billions of years. Denser regions attracted more matter. Matter gathered into filaments. filaments intersected at dense nodes where galaxy clusters formed. Eventually, the universe developed structure resembling gigantic interconnected strands stretching across unimaginable distances. Computer simulations of cosmic evolution reproduce these patterns beautifully. When scientists model dark matter and gravity over billions of years, filamentary structures emerge naturally. The universe organizes itself, not deliberately, not consciously, but inevitably through physical laws operating patiently across cosmic time. One of the most remarkable things about superclusters is how recently humans discovered them properly. For most of history, humanity did not even know galaxies existed beyond the Milky Way. The very idea of structures larger than galaxies is astonishingly modern, and even once astronomers understood galaxies existed everywhere, it still took decades to recognize how they organized themselves. Part of the challenge involved perspective. Human beings observe the universe from inside one galaxy, buried within larger structures. Mapping cosmic geography from inside the system is extremely difficult. It is somewhat like trying to map an entire forest while standing among the trees during foggy weather, while the forest itself slowly moves. Not ideal. Astronomers gradually solved this problem using enormous galaxy surveys. They mapped positions, distances, and motions of galaxies across huge volumes of space. Patterns emerged slowly. Clusters connected to clusters, filaments stretched between them, gigantic voids separated dense regions. The universe stopped looking random. Now, one common misconception about superclusters is imagining them as solid packed walls of galaxies, where the night sky would blaze continuously with light. In reality, even inside dense superclusters, space remains overwhelmingly empty. If the Milky Way and Andromeda collided tomorrow, individual stars would still almost certainly avoid direct collisions because galaxies themselves are mostly emptiness. That emptiness persists even on larger scales. The cosmic web resembles a delicate network more than a crowded city, and yet despite all this emptiness, gravity still sculpts enormous structures because gravity is astonishingly persistent over long timescales. It never tires, never stops, never becomes distracted by social media or forgets why it walked into another room. Gravity simply keeps pulling. Over billions of years, that steady pull builds superclusters. Now, not all superclusters look alike. Some contain particularly rich galaxy clusters near their centers. Others stretch into elongated filaments. Some appear more fragmented or loosely connected. Laniakea itself contains multiple major galaxy clusters connected through large-scale galactic flows. The Virgo cluster represents one important concentration within it, but not the only one. And beyond Laniakea lie other superclusters equally enormous. The observable universe contains countless giant structures spread across billions of light-years, which raises an interesting philosophical question. If superclusters are among the largest structures in existence, does the universe eventually stop organizing itself into larger systems? Apparently yes, at least on the very largest scales observable today. Cosmological observations suggest that beyond certain distances, roughly hundreds of millions of light-years and larger, the universe becomes statistically uniform overall. This idea is called the cosmological principle. In simple terms, although local structures exist, the universe averaged across enormous scales looks roughly similar everywhere. No preferred center exists, no special edge, no cosmic capital city where galaxies gather for important meetings. The universe appears decentralized, which again feels oddly humbling. Now, one reason superclusters fascinate scientists is because they reveal how gravity competes against cosmic expansion. The universe expands because space itself stretches over time due largely to dark energy, the mysterious phenomenon accelerating expansion. But gravity locally fights against this expansion by pulling matter together. Superclusters exist right at this tension point, too large to remain fully stable forever, yet still structured enough for gravity to create coherent flows. This means many superclusters represent temporary stages in cosmic evolution rather than permanent eternal objects. Over trillions of years, dark energy may eventually isolate gravitationally bound clusters from one another permanently as cosmic expansion accelerates. Future observers living unimaginably far ahead in time might see only their local cluster surrounded by darkness while the broader cosmic web disappears beyond the observable horizon. In that future universe, evidence of structures like Laniakea could become impossible to detect, which means humanity exists during a remarkably fortunate cosmological era. We live early enough in cosmic history to still observe the large-scale structure of the universe clearly. There is something almost bittersweet about that. The universe currently reveals itself to us in ways future civilizations may never witness. Now, emotionally speaking, superclusters create a peculiar sensation when contemplated too long late at night. On one hand, they make human life feel very small, tiny even. Earth becomes microscopic inside the Milky Way. The Milky Way becomes microscopic inside Laniakea, and yet there is another perspective available. Human beings are tiny physically, yes, but we are also the part of the universe capable of noticing these structures consciously. The universe produced galaxies. Galaxies produce stars. Stars produce planets. Planets produce chemistry complex enough for life. And eventually, somewhere inside one small spiral arm of one ordinary galaxy, a species evolved capable of mapping superclusters hundreds of millions of light-years wide. That is extraordinary. The atoms inside your brain right now were forged inside ancient stars, long before the Milky Way fully formed its current shape. Those atoms eventually became part of a living creature able to contemplate the structure of the cosmos itself. In a strange way, superclusters are not separate from us. We belong to them physically. Every human being who has ever lived existed inside Laniakea, whether they knew it or not. Ancient kings, farmers, sailors, poets, children staring upward at stars, all drifting together through the same gigantic cosmic structure. And perhaps that continuity explains part of astronomy's emotional power. The universe feels impossibly large, yet we remain connected to it intimately because we emerged from it. Not visitors, participants. If you could somehow rise impossibly far above the universe and watch galaxies move across billions of years, the cosmos would not look still at all. It would flow, slowly, silently, gracefully. Entire galaxies would drift along invisible pathways like leaves floating through enormous dark rivers. Clusters would gather matter from surrounding regions. Filaments would channel galaxies toward dense gravitational basins. Vast empty voids would expand quietly between glowing strands of structure. The universe, on its largest scales, behaves less like scattered objects suspended randomly in space, and more like a giant system of currents. Cosmic weather unfolding over unimaginable time, and those currents played a crucial role in discovering Laniakea supercluster, because astronomers eventually realized something extraordinary. Galaxies are not merely sitting inside superclusters, they are flowing through them. Now, when we think of rivers, we usually imagine water moving downhill across landscapes shaped by gravity. Tiny streams merge into larger streams. Rivers bend through valleys. Eventually, everything drains toward lower regions determined by terrain. The cosmic web behaves surprisingly similarly. Only instead of water, the universe moves galaxies. And instead of mountains and valleys, gravity sculpts invisible landscapes made largely from dark matter. This idea may sound abstract initially, but it becomes much easier to picture once we remember that gravity affects everything with mass continuously. Every galaxy pulls on every other galaxy. Every cluster contributes to the overall gravitational shape of the cosmos. Over immense timescales, these countless interactions create large-scale motions, cosmic flow. One of the reasons this concept feels so strange emotionally is because human beings experience space as mostly static. Buildings stay put, mountains remain where they are, even continents drift slowly enough that individual lives never notice directly. But the universe itself never truly rests. The Earth rotates, the Earth orbits the Sun orbits the centre of the Milky Way moves within the local group flows through Laniakea Supercluster, and Laniakea itself moves relative to other enormous structures in the cosmic web. Everything drifts, everything participates. You're currently travelling through the universe at extraordinary speed, while simultaneously feeling perfectly motionless, sitting in a chair, or lying beneath blankets listening quietly. Which honestly feels slightly unfair from a psychological perspective. Now, astronomers began uncovering these galactic flows gradually during the 20th century, while measuring galaxy velocities. At first, the general expansion of the universe seemed relatively straightforward. Distant galaxies move away because space itself expands. The farther away a galaxy is, the faster it usually recedes. This became known as Hubble's law after Edwin Hubble. But then astronomers noticed deviations. Some galaxies moved slightly faster than expected, others slower. Groups of galaxies appeared drifting together towards certain regions of space. These additional motions became known as peculiar velocities, though there is something charmingly understated about that term. Peculiar velocity sounds like the universe politely apologizing for behaving unexpectedly. In reality, these motions revealed enormous gravitational structures shaping the cosmos. Imagine standing beside a broad river while observing floating leaves. Most leaves drift downstream generally, but local currents create swirls, eddies, and faster channels. By carefully tracking leaf movement, you could infer the shape of the riverbed beneath the surface even if you could not see it directly. Astronomers effectively did the same thing with galaxies. They mapped motion, and motion revealed hidden structure. One especially important breakthrough involved measuring galaxy distances more accurately. Determining how far away galaxies actually are is remarkably difficult, because space is absurdly large, and depth perception stops being useful somewhere around farther than nearby trees. Astronomers developed several techniques for solving this problem. Cepheid variable stars helped first. Then Type 1a supernovae became important because these exploding stars possess predictable brightness levels, useful for measuring enormous distances. Galactic rotation rates also became useful through something called the Tully-Fisher relation discovered partly by Brent Tully. This relationship links how fast spiral galaxies rotate to their intrinsic brightness. Measure rotation and apparent brightness together, and you can estimate distance. Piece by piece, astronomers built three-dimensional maps of nearby galaxies, and once enough data accumulated, the flows became visible. Galaxies streamed toward dense regions. Clusters pulled on neighbouring structures. Matter moved through the universe along giant gravitational pathways. The resulting maps looked astonishingly fluid. Some visualizations resemble glowing rivers crossing darkness. Filaments of galaxies curve through space toward massive nodes like water draining across gigantic cosmic landscapes. Watching these animations creates an odd sensation because the universe suddenly stops feeling static. It starts breathing almost. Not literally, of course. The cosmos is not alive in any biological sense, but there is undeniable motion everywhere, dynamic structure, slow migration unfolding across billions of years. One of the most important regions influencing local galactic flow is the Virgo cluster. The Virgo cluster contains enormous mass, including galaxies, hot gas, and huge amounts of dark matter. Gravity from this region affects motions across vast distances. The local group drifts generally toward Virgo, but Virgo itself is also moving, and beyond Virgo lie even larger gravitational influences. This realization became crucial because astronomers eventually noticed that galactic flows extended beyond the Virgo region entirely. Multiple galaxy clusters and groups appeared participating in larger coherent motion patterns. The cosmic river was larger than expected, much larger. This eventually led scientists toward defining Laniakea Supercluster, based not merely on where galaxies sit spatially, but on how they flow gravitationally. Galaxies inside Laniakea share common motion patterns toward larger attractor regions, and that distinction matters enormously, because it means superclusters are not simply giant piles of galaxies, they are dynamic flow systems. Now, perhaps the strangest feature of these cosmic flows is how strongly invisible matter shapes them. Dark matter dominates large-scale gravitational structure in the universe. Galaxies and clusters form where dark matter concentrations already existed. Matter falls into these gravitational wells gradually over billions of years. Current cosmological models suggest dark matter forms gigantic scaffolding underlying the cosmic web itself. Visible galaxies merely illuminate portions of that hidden framework. This means the rivers of galaxies we observe are guided largely by structures humans cannot see directly, which is wonderfully eerie when contemplated at 2 o'clock in the morning. The visible universe may be only the glowing surface of something much larger and mostly invisible. Still, despite dark matter's invisibility, its effects become measurable through gravity. Astronomers can infer dark matter distributions by observing galaxy motions, gravitational lensing, and large-scale structure formation. Gravity acts like a translator between visible and invisible reality. Now, one particularly fascinating aspect of cosmic flow involves the enormous empty voids between filaments. The universe contains gigantic regions where relatively few galaxies exist at all. Some voids stretch hundreds of millions of light-years across. These voids matter because they help shape flow patterns too. Galaxies tend to move away from emptier regions toward denser ones, much the way rivers drain downhill due to differences in elevation. In cosmic terms, density creates gravitational topography. Dense clusters become valleys, voids become high regions, matter flows accordingly. One reason these structures feel difficult to visualize is because human beings evolved for entirely different scales. Our ancestors needed to understand landscapes spanning perhaps dozens of kilometers. The universe demands understanding structures hundreds of millions of light-years wide. At some point, the brain quietly switches from true comprehension to symbolic approximation. We use metaphors like rivers, webs, and flows because direct visualization becomes almost impossible, and honestly, those metaphors work surprisingly well. The cosmic web truly does resemble drainage networks in many ways. Now, one of the most influential gravitational regions affecting local cosmic flow is the mysterious Great Attractor. For decades, astronomers noticed that the Milky Way, Virgo cluster, and neighbouring structures drifted toward a particular region of space faster than expected. Something massive pulled on everything nearby. The challenge was observation. The Great Attractor lies partly hidden behind the dense stars and dust of the Milky Way itself, in an area sometimes called the Zone of Avoidance. That name sounds wonderfully dramatic, though it mostly means the part where our galaxy blocks the view. Still, improved radio and infrared observations eventually revealed enormous hidden structures beyond the Milky Way, including massive galaxy concentrations like the Norma cluster. The Great Attractor itself may represent not one object but part of a broader gravitational landscape involving multiple massive structures, and galaxies flow toward it, including us. Right now, the Milky Way moves through space at roughly 600 kilometers per second relative to the cosmic microwave background radiation. That motion forms part of these larger cosmic currents. The Earth feels stationary because everything around us shares the same local motion. Much the way passengers inside a smoothly moving airplane often feel still until turbulence reminds them otherwise. Human perception evolved locally. The universe behaves cosmically. Sometimes those two realities feel hilariously mismatched. Now, perhaps the most emotionally striking thing about cosmic flow is how interconnected the universe becomes once motion enters the picture. Galaxies are not isolated islands scattered randomly through emptiness. They influence one another continuously through gravity. Clusters affect neighbouring clusters. Superclusters channel matter along enormous filaments. Everything participates in larger systems, and this interconnectedness emerges naturally from simple physical laws operating patiently across billions of years. Gravity never hurries. It does not need to. Given enough time, even tiny gravitational differences reshape entire regions of the cosmos. There is something calming about that patience. Human life often feels rushed, fragmented, urgent. The universe operates differently. Cosmic structures evolve slowly enough that civilizations rise and disappear, while galaxies barely shift positions noticeably. And yet, eventually gravity carves enormous rivers through the universe itself. Perhaps that is one reason astronomy feels soothing late at night. The cosmos moves with extraordinary calmness. Everything unfolds gradually. Stars burn, galaxies drift, superclusters flow. No panic, no deadlines, just motion. Endless motion shaped by gravity. For most of human history, the universe looked fairly straightforward. You saw stars because stars shine. You saw planets because sunlight reflects from them. You saw galaxies because billions of stars together create enormous glowing structures visible across space. The basic assumption seemed obvious. If something exists, and especially if it has enough mass to shape the cosmos, surely we should be able to see it. Then the universe politely informed astronomers that this assumption was wildly incomplete, because most of the matter shaping cosmic structure appears to be invisible, not hidden behind clouds, not too far away, actually invisible. And without this mysterious invisible matter, structures like Laniakea Supercluster would never have formed at all. Dark matter is one of the strangest ideas in modern science, because it emerged not from imagination or philosophical speculation, but from a simple problem. Galaxies behaved incorrectly, or at least incorrectly according to the amount of visible matter they contained. The first clues appeared during the early 20th century when astronomers began studying galaxy clusters carefully. One especially important figure in this story was Fritz Zwicky, an astronomer famous both for brilliant insights and for being, according to many colleagues, extraordinarily difficult to argue with pleasantly. Zwicky studied the Coma cluster during the 1930s and noticed something deeply strange. The galaxies inside the cluster moved far too quickly. Based on the visible matter alone, the cluster should not have possessed enough gravity to hold itself together. Galaxies moving at those speeds ought to escape the cluster entirely, and yet they remained gravitationally bound. Something unseen contributed enormous additional mass. Zwicky called this missing mass dunkle Materie, dark matter. At the time, many astronomers considered the idea speculative or uncertain. Science often reacts cautiously to invisible things influencing reality dramatically. Which is understandable. Human history contains enough examples of people enthusiastically inventing invisible explanations for things without sufficient evidence. But over the following decades, evidence for dark matter kept accumulating relentlessly. And the universe became stranger. One of the most important breakthroughs came during the 1970s through the work of Vera Rubin. Rubin studied how galaxies rotate. Now, galaxy rotation sounds simple initially. Stars orbit galactic centers much the way planets orbit stars. But the details matter enormously. Imagine our solar system for a moment. Inner planets orbit faster because gravity becomes weaker farther from the Sun. Mercury races around quickly, while Neptune moves much more slowly. Astronomers expected galaxies to behave similarly. Most visible mass in spiral galaxies concentrates toward their centers, so stars farther from the center should orbit more slowly. But when Rubin measured galactic rotation carefully, she found something astonishing. Outer regions of galaxies rotated far too fast. instead of slowing dramatically with distance, rotational speeds remained unexpectedly high, even far beyond visible stellar disks. According to ordinary visible matter calculations, galaxies spinning this rapidly should fly apart, and yet they remained stable. Again, invisible mass appeared necessary, lots of it. The implication was extraordinary. Galaxies sit inside enormous halos of unseen matter extending far beyond visible stars and gas. The glowing portions we see through telescopes may represent only tiny luminous cores embedded within vastly larger invisible structures, which means the visible universe is misleading, beautifully misleading. Astronomy often feels like a story where reality repeatedly turns out much stranger than appearances suggest. Now, as evidence accumulated, dark matter became essential to explaining not just galaxy rotation, but the entire large-scale structure of the universe itself. Without dark matter, galaxies would not form properly, clusters would not remain stable, superclusters like Laniakea supercluster would never emerge. Current cosmological models suggest dark matter outweighs ordinary visible matter by roughly 5 to 1. Think about that for a moment. Everything humans directly interact with, stars, planets, oceans, trees, cities, cats knocking objects off tables for unclear reasons, all of it together represents only a small fraction of the universe's total matter content. Most matter appears invisible, and this invisible matter forms the hidden skeleton of the cosmos. That phrase, hidden skeleton, is not merely poetic, it is scientifically accurate in many ways. Dark matter shapes gravitational landscapes across the universe. Ordinary matter falls into dark matter structures gradually over billions of years, eventually forming galaxies and clusters where dark matter concentrations already existed. Computer simulations demonstrate this beautifully. When astronomers model the universe using only ordinary visible matter, large-scale structures fail to form correctly. Galaxies emerge too slowly. Clusters do not match observations, but when dark matter gets included, suddenly the cosmic web appears naturally. Filaments stretch across space, clusters gather at intersections, voids emerge between structures, the simulated universe begins resembling reality. Dark matter acts like scaffolding, invisible gravitational architecture beneath everything we observe, and nowhere does this become more important than in gigantic structures like Laniakea. Now, one reason dark matter feels emotionally unsettling is because human beings evolved, assuming reality consists mostly of things we can perceive directly. That assumption worked reasonably well for survival on ancient grasslands. Large predators generally benefit from being visible. Hidden cosmic matter shaping galaxies across billions of light years was less immediately relevant to survival priorities. So the human brain still instinctively equates visibility with reality. Dark matter breaks that instinct completely. Most of the gravitational universe remains invisible. Still, although dark matter cannot be seen directly, astronomers detect its effects constantly. Gravity exposes it. One especially fascinating method involves something called gravitational lensing. According to Albert Einstein and general relativity, massive objects warp space-time itself. Light travelling through curved space-time bends accordingly. This means galaxy clusters can act like enormous gravitational lenses, distorting light from more distant galaxies behind them. Astronomers observe these distortions regularly, and the amount of bending often exceeds what visible matter alone could produce. Again, invisible mass appears necessary. Sometimes lensing creates extraordinary visual effects. Background galaxies stretch into arcs or multiple images around massive clusters. Space itself becomes visibly warped by gravity. The universe occasionally behaves less like classical astronomy and more like surreal abstract art produced by geometry itself. Now, despite decades of evidence, nobody yet knows exactly what dark matter is made of. That remains one of the greatest unsolved problems in physics. Scientists know what dark matter does gravitationally. They know it interacts weakly, or perhaps not at all, with light. But its true nature remains mysterious. Several possibilities exist. Some theories propose undiscovered particles called WIMPs, weakly interacting massive particles. Others suggest axions, hypothetical ultralight particles. Some researchers explore sterile neutrinos. More speculative ideas involve modifications to gravity itself rather than unseen matter. So far, direct detection experiments have not conclusively identified dark matter particles, and astronomers keep searching. Deep underground laboratories attempt to detect rare interactions between dark matter and ordinary matter. Giant detectors buried beneath mountains wait patiently for faint signals. Particle accelerators probe high-energy physics searching for clues. The hunt continues, which means one of the most important ingredients shaping the universe remains fundamentally unknown. That fact alone says something remarkable about humanity's current place in scientific history. We have mapped galaxies billions of light-years away. We have photographed black hole shadows. We have detected gravitational waves from colliding black holes. And yet we still do not fully understand most of the matter in the universe. Reality remains gloriously unfinished. Now, when astronomers map structures like Laniakea Supercluster, dark matter becomes unavoidable because ordinary visible galaxies alone cannot explain the observed motions. Galaxies flow through gravitational landscapes dominated largely by invisible mass. The cosmic rivers discussed earlier follow valleys carved primarily by dark matter distributions. This means that when we admire images of galaxies and superclusters, we are actually seeing only the illuminated tips of vastly larger structures hidden beneath, almost like frost tracing invisible currents across a window pane, or glowing cities revealing the outlines of continents at night. Visible matter marks where dark matter shaped the universe most strongly, and this hidden structure extends everywhere. Dark matter halos surround galaxies. Dark matter filaments connect clusters. Dark matter shapes the cosmic web itself. Even the Milky Way sits embedded inside a huge dark matter halo, extending far beyond visible stars. Right now, as you listen quietly somewhere on Earth, enormous amounts of dark matter pass through your body continuously without interaction. That sounds alarming initially. Fortunately, dark matter barely interacts with ordinary matter except through gravity. Otherwise, the universe would behave far more inconveniently. Still, there is something wonderfully eerie about existing inside invisible cosmic structure constantly. The universe feels less empty once you realize most of it simply cannot be seen. Now, one particularly important role of dark matter involves stabilizing structure formation over cosmic time. The early universe after the Big Bang contained tiny density fluctuations. Dark matter helped amplify these fluctuations gravitationally because it began clumping earlier than ordinary matter. Ordinary matter initially remained tightly coupled to radiation in the hot young universe. Dark matter did not. This allowed dark matter structures to start forming first. Later, ordinary matter fell into these gravitational wells, eventually producing stars and galaxies. In a sense, dark matter prepared the stage before visible cosmic structure arrived. Without it, the universe might remain much smoother and emptier. No galaxies, no clusters, no superclusters, possibly no planets, no people. No sleepy astronomy videos at night discussing invisible matter while trying not to think too hard about how strange existence really is. Dark matter helped make complexity possible, and complexity eventually became conscious. Now, despite its mystery, dark matter also creates a surprisingly comforting perspective about the universe. Human beings often assume that what we perceive represents reality fully, but science repeatedly reveals deeper layers hidden beneath appearances, atoms beneath solid matter, genes beneath inheritance, gravity beneath falling objects, dark matter beneath cosmic structure. Reality contains more than immediate perception suggests, and perhaps that idea extends beyond cosmology too. There are places in the universe that feel almost mythical the moment you hear about them. Black holes, dark matter, the edge of the observable universe. And somewhere on that list sits one of the strangest large-scale structures astronomers have ever encountered. Great Attractor. Even the name sounds dramatic, like something ancient civilizations would build temples around, or perhaps the title of a science fiction novel written by someone who drinks too much coffee and distrusts ordinary geometry. But the Great Attractor is real, or at least the gravitational effects associated with it are undeniably real. Entire galaxies, including the Milky Way itself, appear drifting toward this enormous gravitational region hidden deep behind the dense stars and dust of our own galaxy. And for decades, astronomers struggled to understand exactly what was pulling everything in that direction. To appreciate how strange this discovery was, we first need to remember something important about the expanding universe. On the largest scales, galaxies generally move away from one another because space itself expands. This expansion was one of the great discoveries of 20th century astronomy. The farther away galaxies are, the faster they tend to recede. That is the average behavior. But galaxies also possess local motions caused by gravity. These local motions become extremely important because gravity never truly disappears. Massive structures tug continuously on surrounding matter. Galaxy clusters pull on neighbouring clusters. Superclusters influence enormous regions across space. And eventually astronomers notice something peculiar about our own motion. The local group was not simply participating in ordinary cosmic expansion. It was moving in a specific direction unusually fast. Now, when astronomers measure cosmic motion, they often compare things relative to something called the cosmic microwave background radiation, the faint afterglow left behind from the early universe after the Big Bang. This radiation fills the universe almost uniformly. Almost. Because motion changes how we perceive it. If you move toward one region of the cosmic microwave background, that region appears slightly hotter due to Doppler shifting. Move away, and another region appears slightly cooler. By measuring these tiny temperature differences, astronomers can determine how fast our galaxy moves relative to the broader universe. And the answer was startling. The Milky Way and the local group move at roughly 600 kilometers per second toward a particular region of space. That is more than 2 million kilometers per hour. Yet because everything around us shares this motion locally, we feel absolutely nothing. Human beings are remarkably good at ignoring cosmic absurdity during ordinary daily routines. You can brush your teeth while drifting through space toward an enormous gravitational anomaly without the slightest sensation of inconvenience. Now, once astronomers identified this motion, they naturally began asking what exactly was causing it. Gravity requires mass, lots of mass. Something enormous had to exist in that direction, pulling galaxies toward it. At first, the Virgo cluster seemed like the obvious explanation. The Virgo cluster is massive enough to influence neighbouring structures significantly, and indeed, it does contribute to local galactic flow. But calculations eventually showed Virgo alone could not explain the full motion observed. Something larger lurked farther beyond. And this is where the story becomes especially difficult, because the region involved lies behind the plane of the Milky Way itself. Our galaxy contains huge amounts of dust, gas, and stars concentrated along its disk. When astronomers observe outward through that dense galactic plane, visibility becomes severely limited. Dust blocks visible light almost completely in some directions. This obscured region became known as the zone of avoidance, which sounds wonderfully mysterious but essentially means the part where the Milky Way is in the way. It is a bit like trying to map distant mountain ranges while standing inside a brightly lit forest during foggy weather. You know something exists beyond the obstruction. You simply cannot see it clearly. Still, astronomers are persistent creatures. Give scientists an obstructed view, and they immediately begin inventing new methods to peer through it. Radio telescopes helped. Infrared observations helped. X-ray astronomy helped. Gradually, hidden structures beyond the Milky Way began emerging from the darkness, and what astronomers found was astonishing. Massive galaxy clusters, gigantic concentrations of matter, enormous structures hidden behind our galaxy's dusty foreground. One especially important discovery involved the Norma Cluster, an enormous galaxy cluster lying near the center of the Great Attractor region. The Norma Cluster contains thousands of galaxies and tremendous amounts of mass. It became clear that this region represented one of the densest nearby concentrations of matter in the local universe. Yet even that might not fully explain everything. Because the Great Attractor itself appears to be part of an even larger network of gravitational structures stretching across immense distances. In other words, the more astronomers studied the Great Attractor, the less it behaved like one single object, and the more it resembled part of a gigantic gravitational landscape shaping galactic flows across huge regions of space. And this eventually tied directly into the discovery of Laniakea Supercluster. Galaxies inside Laniakea drift through enormous cosmic currents, partly influenced by the gravitational pull of these dense regions. The universe began looking less like isolated objects scattered randomly through emptiness, and more like an interconnected flow system guided by gravity. Now, perhaps the strangest thing emotionally about the Great Attractor is how invisible it feels. Human beings naturally associate importance with visibility. Mountains look imposing because we can see them towering overhead. Oceans feel immense because they stretch visibly to horizons. But the Great Attractor announces itself mostly through motion. We infer its presence because galaxies move toward it, including us. There is something deeply unsettling and fascinating about realizing the Milky Way itself drifts toward an enormous hidden gravitational region beyond direct sight. And the distances involved are staggering. The Great Attractor region lies roughly 150 to 250 million light-years away, depending on exactly which structures get included. Light reaching us from there tonight began travelling before the first dinosaurs appeared on Earth. Meanwhile, gravity from that region has influenced our galactic motion across enormous stretches of cosmic history. One of the reasons this story captured public imagination so strongly is because it sounds almost personal somehow. The Great Attractor feels less like a technical astronomical phenomenon, and more like a mysterious destination pulling entire galaxies toward itself, which, scientifically speaking, is not entirely wrong. Still, it is important to understand that gravity here operates collectively. No single object drags galaxies inward like a cosmic vacuum cleaner. Instead, enormous concentrations of mass shape space-time across huge distances, guiding galactic flows gradually over billions of years. Everything happens slowly, very slowly. The local group will not suddenly plunge dramatically into the Great Attractor tomorrow afternoon between lunch and checking emails. Cosmic motion unfolds patiently. Yet these motions matter enormously because they reveal the underlying structure of the universe itself. By studying galactic flow toward regions like the Great Attractor, astronomers could map the hidden gravitational terrain surrounding us. That work helped redefine our understanding of superclusters and eventually contributed to identifying Laniakea as one gigantic flow basin. In a sense, the Great Attractor acts like one of the deep valleys shaping the rivers of galaxies moving through our region of the cosmos. Now, one especially interesting twist in this story arrived when astronomers discovered even larger structures beyond the Great Attractor itself, because apparently the universe never misses opportunities to become more excessive. Farther away lies something called the Shapley Supercluster, one of the largest mass concentrations in the nearby observable universe. The Shapley Supercluster may contribute significantly to the motions previously attributed solely to the Great Attractor, which means our cosmic neighbourhood may be influenced by multiple gigantic structures, tugging simultaneously across hundreds of millions of light-years. Gravity becomes complicated at these scales, very complicated. Entire superclusters interact through enormous overlapping gravitational fields, while cosmic expansion simultaneously stretches space itself. The universe behaves less like neat clockwork and more like an evolving ecosystem of motion and influence. And hidden beneath much of it lies dark matter shaping everything invisibly. Now, emotionally speaking, the Great Attractor creates a curious feeling once you sit with the idea long enough. The Milky Way feels enormous from human perspectives. Hundreds of billions of stars, 100,000 light-years across. And yet our entire galaxy drifts through space influenced by structures so massive they reduce the Milky Way to one small moving participant among countless others. The scale becomes almost impossible to hold mentally. Still, perhaps there is comfort in realizing movement itself is universal. Nothing truly stands still. Not planets, not stars, not galaxies, not superclusters. Everything belongs to larger systems. Everything responds to gravity. Even human life reflects this in smaller ways. People drift through cities, relationships, histories, and cultures shaped by forces larger than themselves. We rarely see the full structures influencing our paths clearly while living inside them. The universe behaves similarly. Galaxies follow invisible currents shaped by gravitational landscapes, too large to perceive directly from within. And despite all this motion, ordinary life continues calmly on Earth. People sleep, dream, drink tea, miss appointments, watch stars. The cosmos remains unimaginably vast while human existence stays beautifully local. Perhaps that contrast explains why astronomy feels soothing rather than frightening for many people. The universe becomes so large that anxiety starts losing its grip slightly. Problems remain real, certainly, but cosmic scale gently rearranges perspective, and the Great Attractor is a perfect example of that rearrangement. An enormous hidden gravitational region influencing entire galaxies across hundreds of millions of light-years. Yet tonight, somewhere on Earth, someone is probably lying awake worrying about whether they worded an email incorrectly. Human beings are wonderfully small-scale creatures inside gigantic cosmic structure. Once human beings understood that galaxies gather into clusters, and clusters gather into superclusters, like Laniakea Supercluster, a natural question followed. What does the universe actually look like when viewed on the largest scales possible? Not from Earth, not from inside the Milky Way, but from impossibly far away. If some distant observer could step outside the local cosmos and look across billions of light-years all at once, what would they see? For a long time, astronomers genuinely did not know. Early ideas about the universe varied wildly. Some scientists imagined galaxies scattered randomly through endless space like dust floating in sunlight. Others suspected larger patterns existed but lacked enough observational data to prove it. And honestly, this uncertainty makes perfect sense because the universe is extremely difficult to map from the inside. Human beings occupy one small planet orbiting one ordinary star buried inside one galaxy among hundreds of billions. Trying to reconstruct the structure of the cosmos from that position is a bit like attempting to map the entire Earth while trapped inside a moving elevator with fogged windows. You collect clues patiently, tiny glimpses, partial patterns, and over time an image slowly emerges. What astronomers eventually discovered was more beautiful and stranger than almost anyone expected. The universe has structure, enormous structure, not chaotic randomness, not perfect order either, something in between. On the largest scales, galaxies arrange themselves into gigantic filaments, stretching across space like glowing threads. These filaments connect dense clusters and superclusters while surrounding vast, nearly empty regions called cosmic voids. Together, these patterns form what scientists call the cosmic web, and the cosmic web is one of the most astonishing things humanity has ever discovered. Now, the phrase cosmic web sounds poetic enough that people sometimes assume astronomers invented it, mainly because scientists secretly enjoy dramatic naming opportunities. But in this case, the name is genuinely accurate. When astronomers map millions of galaxies across huge volumes of space, the resulting structures truly resemble an enormous web or network. Filaments intersect like strands. Clusters gather at dense nodes. Immense voids open between them. The universe begins looking almost organic. Not alive biologically, of course. Galaxies are not cells communicating intentionally through space while holding committee meetings about gravitational policy. But visually, the patterns become surprisingly similar to structures found elsewhere in nature. Neural networks, river systems, fungal growth, foam bubbles. Nature repeatedly creates networks when matter and energy organize themselves through simple physical rules. Gravity happens to be extremely good at building cosmic networks. Now, one important thing to understand is that the universe only appears web-like on gigantic scales. Locally, space still looks mostly empty. If you travel from Earth outward, you encounter enormous stretches of near vacuum. The nearest star beyond the Sun sits over 4 light-years away. Galaxies themselves remain separated by millions of light-years. Even inside galaxy clusters, individual galaxies rarely collide directly because the distances between stars are so vast. Space is mostly emptiness. Yet gravity slowly shapes this emptiness into patterns over billions of years. The story begins shortly after the Big Bang. The early universe was incredibly hot, dense, and surprisingly smooth overall. Matter spread through space almost evenly. Almost. Tiny fluctuations existed, slight regions where matter density was a little higher than average. These fluctuations were incredibly small, tiny differences in density preserved today in the cosmic microwave background radiation. Yet those minute irregularities became the seeds of all later cosmic structure. Gravity amplified them patiently. Denser regions attracted more matter. More matter increased gravity further. Small clumps grew larger. Eventually, dark matter formed enormous invisible structures stretching across space. Ordinary matter later fell into these gravitational wells, forming stars, galaxies, and clusters. Over billions of years, the cosmic web emerged naturally. One of the most fascinating aspects of this process is how dependent it was on dark matter. Without dark matter, the universe would likely look dramatically different, much smoother. Less structured. Galaxies might struggle to form efficiently at all. Dark matter acts like invisible scaffolding underlying the entire cosmic web. The visible galaxies we observe merely illuminate portions of a much larger hidden framework. In a sense, the universe we can see is only the glowing skin of something far larger and mostly invisible, which feels wonderfully unsettling late at night. Now, astronomers began uncovering the cosmic web gradually during the 20th century as galaxy surveys improved. Early maps already hinted that galaxies cluster together unevenly, but the true scale of cosmic structure only became clear once astronomers gathered enormous amounts of data. One particularly important project was the Sloan Digital Sky Survey. The Sloan survey mapped millions of galaxies across huge regions of space with extraordinary precision. And when scientists visualized the data, the universe transformed from random scatter into giant interconnected structure. Filaments stretched hundreds of millions of light years, clusters gathered at intersections, voids opened like gigantic cosmic bubbles between denser regions. The resulting maps became some of the most extraordinary images in modern science. Not because they were colourful exactly. Many cosmic web maps appear fairly simple visually, but because they revealed humanity's place inside a structure so vast that ordinary thought begins malfunctioning trying to process it. Our galaxy became one tiny node inside a gigantic cosmic network, and the network itself extended farther than human intuition comfortably tolerates. Now, one of the most interesting features of the large-scale universe is that despite all these enormous structures, the cosmos becomes statistically uniform at sufficiently large scales. This idea is called the cosmological principle. Essentially, although local structures exist, the universe averaged across huge enough distances appears roughly the same everywhere. No special center exists, no preferred direction, no cosmic throne room where important galaxies gather to discuss universal affairs. From almost any sufficiently large perspective, the universe would look broadly similar. That realization carries deep philosophical implications. Human beings instinctively seek centers. Ancient civilizations placed Earth at the center of creation. Later we learned Earth orbits the Sun. Then the Sun became one ordinary star. Then the Milky Way became one ordinary galaxy. And now even superclusters like Laniakea Supercluster appear as only small pieces of a much larger cosmic web without any overall center at all. The universe does not organize itself around us, and strangely, many people find that comforting rather than depressing, perhaps because decentralization makes existence feel shared rather than hierarchical. Now, one particularly fascinating aspect of the cosmic web involves the gigantic voids between filaments. These voids are enormous regions containing very few galaxies compared to average cosmic density. Some stretch hundreds of millions of light years across. Imagine that scale for a moment. Not empty rooms, not empty solar systems, regions of near emptiness larger than entire superclusters. If galaxy filaments are cosmic cities, voids are unimaginable wildernesses, and yet voids matter enormously because they help shape cosmic flow. Matter drains away from less dense regions toward denser ones. Reinforcing the web-like structure over time, the universe evolves dynamically. Clusters grow, filaments strengthen, voids expand, everything changes gradually. One reason the cosmic web fascinates scientists so deeply is because it provides clues about the universe's fundamental composition and evolution. The shape of large-scale structure depends sensitively on dark matter, dark energy, and conditions in the early universe. By studying cosmic structure carefully, astronomers can test cosmological models and refine understanding of how the universe evolved from the Big Bang into its current form. In a sense, the cosmic web acts like a fossil record of cosmic history. Its structure preserves information about ancient processes unfolding billions of years ago. Now, emotionally speaking, the cosmic web creates a very particular feeling once you spend enough time contemplating it. At first, it makes humanity feel small, ridiculously small. Earth disappears entirely at these scales. Even galaxies become tiny dots along filaments stretching across incomprehensible distances. But then another feeling often follows: connection. Because the cosmic web reveals that nothing truly exists in isolation. Galaxies influence one another gravitationally across enormous distances. Clusters connect through filaments. Matter flows through the universe along gigantic invisible pathways. The cosmos behaves less like separate objects and more like one evolving system, and we belong to it physically. Every atom inside your body emerged from cosmic processes unfolding inside this web. Ancient stars forged the carbon, oxygen, calcium, and iron composing human beings today. The universe built structure gradually over billions of years, until eventually life appeared capable of noticing the structure itself. That alone feels extraordinary enough to sit quietly with for a while. Right now, somewhere inside one small spiral arm of one ordinary galaxy, a conscious creature is thinking about the large-scale structure of the cosmos. That sentence would sound absurd to most of human history, and yet, here we are. Now, perhaps the most beautiful thing about viewing the universe on its largest scales is how it changes our relationship with ordinary life. Human problems remain real, certainly. Bills still exist. People still get tired, anxious, lonely, overwhelmed. Astronomy does not erase human experience, but it reframes it gently. The cosmic web reminds us that existence itself is astonishingly unlikely and interconnected. Every human being who has ever lived existed inside this gigantic structure, whether they knew it or not. Ancient farmers, kings, sailors navigating by stars, children looking upward wondering what galaxies were before the word galaxy even existed, all drifting together through the same cosmic web. And perhaps that continuity matters, because on the larger scales the universe does not look hostile exactly. It looks structured, ordered enough for galaxies to form, stable enough for stars to burn billions of years, complex enough for life eventually to emerge. The cosmic web is not random chaos. It is gravity-shaping possibility across time. Still, the universe continues evolving. And one of the strangest questions astronomers now ask about structures like Laniakea Supercluster is whether they are permanent at all. One of the strangest things about the universe is that even its largest structures may not last forever. Human beings often imagine enormous things as permanent by default. Mountains feel eternal, oceans seem timeless, galaxies themselves appear stable because their motions unfold so slowly compared to human life. And then astronomy quietly reminds us that permanence is mostly an illusion created by limited lifespans. Stars die, galaxies collide, black holes evaporate eventually. Even structures as enormous as Laniakea Supercluster may already be slowly coming apart, which is a rather unsettling sentence when you first hear it, because Laniakea feels impossibly huge from human perspectives. It stretches roughly 520 million light-years across and contains around 100,000 galaxies connected through enormous gravitational flows. Surely something that large must be stable. Surely gravity holds it together permanently. Well, not exactly. And the reason comes down to one of the most mysterious discoveries in modern cosmology. The universe is not merely expanding, its expansion is accelerating. Now that statement deserves a slow explanation because it completely changed astronomy during the late 20th century. For much of scientific history, astronomers assumed cosmic expansion should gradually slow down over time. Gravity pulls matter together. Galaxies attract one another, so the expansion left over from the Big Bang ought to weaken eventually. That expectation seemed perfectly reasonable. Imagine throwing a ball upward from Earth. Gravity slows the ball continuously until eventually it stops rising and falls back down. Astronomers once imagined the universe behaving similarly. Expansion should decelerate gradually under the influence of gravity. The only uncertainty involved how much matter existed. If the universe contained enough matter, gravity might eventually halt expansion completely and reverse it in a catastrophic collapse sometimes called the Big Crunch. If too little matter existed, expansion would continue forever while slowing gradually. Those seemed like the main possibilities. Then the universe did something deeply rude to everyone's expectations. During the 1990s, astronomers studying distant supernovae discovered that the expansion of the universe is actually speeding up, not slowing, speeding up, and nobody saw that coming. The discovery emerged from observations of Type 1a supernovae, exploding stars useful as cosmic distance markers because they possess fairly predictable brightness levels. By comparing how bright these supernovae appeared with how much their light had shifted due to cosmic expansion, astronomers could estimate how the expansion rate changed over time. The results were shocking. Distant galaxies appeared farther away than expected. The universe had expanded more rapidly over time than gravity alone could explain. Something mysterious pushed space itself apart. Scientists eventually gave this unknown phenomenon a simple name: dark energy, which admittedly sounds less like a rigorous scientific term and more like a rejected perfume brand marketed toward emotionally unavailable astrophysicists. Still, dark energy became essential because observations consistently supported accelerated expansion, and today, dark energy appears to dominate the large-scale behavior of the universe. Current cosmological estimates suggest roughly 68% of the universe consists of dark energy. Dark matter contributes around 27%. Ordinary visible matter, stars, planets, gas, dust, people awkwardly overthinking text messages late at night, all of that together makes up only about 5%, which means the familiar visible universe represents a tiny fraction of cosmic reality, again. Astronomy truly enjoys reminding humanity how incomplete our intuitions are. Now, dark energy matters enormously for structures like Laniakea Supercluster, because it determines whether enormous cosmic structures remain gravitationally bound over time. Smaller systems can resist expansion locally through gravity. The Earth remains bound to the Sun. The Sun remains bound inside the Milky Way. The Milky Way and Andromeda Galaxy continue moving toward one another despite cosmic expansion because gravity dominates locally. But on larger scales, dark energy becomes increasingly important, and superclusters sit right at this delicate boundary between gravity and expansion. This creates a fascinating possibility. Laniakea may not actually be one stable, permanently bound object. Instead, it may represent a temporary large-scale flow structure, gradually evolving while cosmic expansion slowly pulls parts of it apart. In other words, some regions inside Laniakea may never fully collapse together gravitationally, because dark energy drives space apart faster than gravity can unite everything permanently. That idea feels deeply strange emotionally, because human intuition assumes large structures remain stable automatically. Yet the universe operates differently. Size alone does not guarantee permanence. Now, to understand this better, it helps to think about cosmic structure hierarchically. Galaxies themselves usually remain gravitationally bound internally. The Milky Way will not suddenly dissolve because dark energy overwhelms it. Gravity inside galaxies is far too strong on those scales. Galaxy clusters also often remain gravitationally bound. Clusters contain enormous amounts of matter, concentrated densely enough for gravity to dominate locally. But superclusters are more diffuse. Galaxies inside them can lie separated by huge distances. Their mutual gravitational binding becomes weaker overall. This means superclusters may behave more like temporary traffic patterns than permanent cosmic buildings. Matter flows together for a while, structures emerge, then expansion gradually stretches larger regions apart again. One especially important consequence involves the future visibility of the universe itself. Right now, human beings live during a remarkably fortunate cosmic era. We can still observe distant galaxies clearly. The cosmic web remains visible. Structures like Laniakea can still be mapped, but dark energy changes everything over sufficiently long time scales. As expansion accelerates, distant galaxies recede faster and faster. Eventually some become unreachable, even by light travelling forever because space itself expands too rapidly between us. This creates something called the cosmic horizon. Galaxies beyond this horizon effectively disappear from the observable universe over time. Future civilizations living trillions of years from now may see dramatically less of the cosmos than we do today. Imagine astronomers in that distant future. The local group will likely have merged into one giant elliptical galaxy by then. Most other galaxies beyond the local group may have vanished beyond the cosmic horizon entirely. The night sky would appear far emptier. Future astronomers might struggle to discover cosmic expansion at all, because evidence for the larger universe would largely disappear from view. In some ways, humanity lives during the best possible era for cosmology. The universe still reveals its large-scale structure clearly enough for discovery. That fact feels almost bittersweet. Now, regarding Laniakea specifically, astronomers continue debating how gravitationally bound the structure truly is. The definition of superclusters themselves becomes complicated because cosmic expansion and gravitational flow interact across enormous scales. Some scientists argue that only smaller regions inside Laniakea will remain permanently bound over cosmic time, while broader parts drift apart gradually. Others focus less on long-term permanence and more on present-day flow structure. This distinction matters scientifically. A supercluster can still represent a meaningful physical structure even if it does not remain intact forever. After all, hurricanes exist despite being temporary. River systems exist despite constantly changing. Galaxies themselves evolve continuously through mergers and star formation. Nature rarely builds eternal structures. Instead, it creates patterns persisting for certain timescales before transforming into something else. The universe appears comfortable with impermanence. Human beings, meanwhile, spend considerable emotional energy pretending otherwise. Still, perhaps there is comfort hidden inside cosmic impermanence too. Laniakea does not become less beautiful because it evolves. In fact, its gradual transformation makes it feel more alive somehow. Not alive biologically, but dynamic, active, participating in cosmic history rather than frozen outside time. Everything changes. Stars burn out, galaxies merge, superclusters drift, even space-time itself evolves. The universe is less a static object and more an unfolding process. Now, one particularly fascinating implication of accelerated expansion involves the ultimate future of cosmic structure. If dark energy continues behaving as it currently appears to, then over unimaginable timescales, the universe may become increasingly isolated. Clusters separated from other clusters, galaxies disappearing beyond horizons, the cosmic web thinning observationally until local gravitational systems remain as lonely islands surrounded by darkness. This scenario is sometimes called the Big Freeze or heat death of the universe. Not because everything becomes icy exactly, although temperatures do decrease generally, but because usable energy gradually spreads out more evenly over time. Stars eventually die. Black holes evaporate through Hawking radiation over absurdly long timescales. Matter decays possibly. The universe trends toward increasing entropy. And yet despite all this distant cosmic melancholy, the present universe remains astonishingly active and beautiful. Stars continue forming. Galaxies continue colliding. Life continues emerging. Human beings continue existing inside a cosmic era, rich enough for consciousness to contemplate structures like Laniakea Supercluster at all. That alone feels remarkable. Right now, somewhere inside one small galaxy flowing through a possibly temporary supercluster, conscious creatures have learned enough physics and astronomy to realize the impermanence of structures hundreds of millions of light-years wide. The universe evolved matter capable of understanding its own large-scale future, which is honestly extraordinary. Now, emotionally speaking, astronomy's lessons about impermanence can initially feel unsettling. People naturally seek stability. Permanence feels comforting. But the cosmos repeatedly reveals that change is fundamental. Nothing stays fixed forever. And perhaps that is not entirely tragic. After all, impermanence also allows evolution, growth, complexity, and life itself. A perfectly static universe would likely contain no stars, no chemistry, no planets, no consciousness. Motion and change create possibility. Even Laniakea exists because the universe evolves. Galaxies flow together. Gravity sculpted structure. Dark matter built invisible scaffolding. And for a while, cosmic rivers formed one enormous interconnected basin we now call home. Temporary, perhaps, but real nonetheless. And maybe that is enough. Because whether Laniakea survives eternally or slowly dissolves over billions of years, the fact remains that right now, at this moment in cosmic history, we exist inside one of the largest known structures in the universe. A structure so enormous that ancient civilizations could never have imagined it. Yet somehow, here we are, small conscious beings drifting through it together, and that realization changes the feeling of the night sky forever. There is a particular kind of loneliness that only appears when human beings begin understanding the true scale of the universe. Not ordinary loneliness, not the feeling of sitting alone in a quiet room while rain taps against windows or while distant traffic hums softly outside at night. This is something stranger, a kind of cosmic loneliness. The realization that Earth is small, the solar system is small, the Milky Way is small. Even Laniakea Supercluster, a structure spanning more than 500 million light-years, may itself be only one thread among countless others woven through the cosmic web. At first, these discoveries can feel emotionally overwhelming. Human beings evolve for villages, for tribes, for landscapes small enough to cross on foot. Our ancestors survived by understanding rivers, seasons, nearby forests, and the expressions on other human faces. Evolution prepared the human brain wonderfully for avoiding predators and remembering where berries grew. It didn't prepare us particularly well for emotionally processing structures containing 100,000 galaxies. And yet here we are anyway. Tiny, conscious creatures trying to imagine the architecture of the cosmos before falling asleep at night, which honestly may be one of the strangest things the universe has ever produced. Now, one common reaction to cosmic scale is a feeling of insignificance. People hear about superclusters, cosmic voids, billions of galaxies, and suddenly ordinary human life begins feeling microscopic by comparison. Your worries shrink, your ambitions shrink. Sometimes even your identity feels strangely fragile against the backdrop of cosmic immensity. And to be fair, astronomy absolutely does reduce human physical importance in certain ways. The Earth is not the centre of the universe. The Sun is not special. The Milky Way is not unique. Laniakea itself is not uniquely important either. The universe does not appear organised around humanity at all. Yet something interesting often happens. After that initial emotional shock fades, the loneliness changes shape. Because the deeper astronomy explores the cosmos, the more interconnected everything starts becoming. Nothing exists entirely alone. Not planets, not stars, not galaxies. Everything belongs to larger systems. Earth belongs to the solar system. The solar system belongs to the Milky Way. The Milky Way belongs to the local group. The local group flows through Laniakea, and Laniakea itself forms part of the cosmic web stretching across the observable universe. We are tiny, but we are also connected. Perhaps both are true simultaneously. Now, this strange tension between insignificance and connection becomes especially fascinating when people begin asking unusual questions about large-scale cosmic structure. Questions that sound philosophical at first, or even slightly ridiculous. Questions like this: could the universe itself, on sufficiently large scales, behave almost like something alive? Now, before we continue, it is important to say clearly that according to current science, superclusters are not alive in the biological sense. Laniakea supercluster is not conscious. It does not think. It does not possess intentions, emotions, desires, or awareness. Galaxies are not neurons sending messages deliberately through space. And yet, the comparison continues appearing over and over again in both science and philosophy, because large-scale cosmic structure behaves in ways that feel strangely organic, not literally alive, but structurally familiar. The cosmic web resembles neural networks visually. Matter flows through filaments, almost like nutrients through biological systems. Gravity organizes enormous structures dynamically over time. Clusters gather, evolve, merge, and interact. The universe develops complexity gradually through self-organization, and human beings notice these similarities instinctively. One reason this happens is because nature often produces similar patterns across wildly different scales, whenever simple physical rules repeat consistently. River systems branch, blood vessels branch, lightning branches, tree roots branch, galactic filaments branch. The universe seems deeply fond of networks. Now, occasionally sensational headlines appear claiming the cosmic web looks exactly like the human brain. That comparison gets exaggerated sometimes. The similarities are mostly visual and mathematical, rather than evidence of any literal cosmic consciousness. Still, the resemblance remains intriguing. Studies comparing network structures have shown that both neural systems and cosmic web structures share certain statistical similarities in how connections distribute themselves. Again, this does not mean the universe is secretly a giant brain, though admittedly that would make awkward social interactions feel considerably more understandable. What it does suggest is that certain forms of complexity emerge naturally whenever matter organizes through physical laws across large systems. Nature reuses successful patterns. Now, perhaps the most emotionally interesting question is not whether superclusters are biologically alive, but whether life itself may simply represent one stage of increasing cosmic complexity. Because when you step back far enough, the universe begins looking less like random chaos and more like an evolving process. The early universe after the Big Bang contained mostly simple particles and radiation. Then came atoms, then stars, then galaxies, then heavier chemical elements forged inside stars, then planets, then chemistry complex enough for biology, then nervous systems, then consciousness, and eventually creatures capable of mapping structures like Laniakea Supercluster. The universe became aware of itself through living systems, not necessarily intentionally, but physically. Consciousness emerged from cosmic evolution. That idea alone can completely rearrange how the night sky feels emotionally. You're not separate from the universe observing it from outside. You are one small piece of the universe temporarily capable of reflection. The atoms inside your body were forged in ancient stars billions of years ago. The calcium in your bones, the oxygen you breathe, the iron in your blood, all emerged from stellar processes long before Earth existed. Human beings are made from cosmic history physically. Now, this perspective creates a curious emotional paradox. Astronomy makes us feel small physically, while simultaneously making us feel deeply connected cosmically. Perhaps that is why space can feel comforting late at night rather than frightening. The universe becomes too vast for ego to remain inflated comfortably. Yet it also becomes too interconnected for true isolation to survive entirely. Even loneliness starts changing shape, because every human being who has ever existed lived inside the same cosmic structures. Ancient peoples staring upward at stars from deserts, forests, mountaintops, ships, villages and cities all belong to the same galaxy, the same local group, the same Laniakea supercluster. They simply did not know the names yet. And perhaps somewhere tonight on another planet orbiting another star inside another galaxy, another civilization may also be discovering these structures gradually. Imagine that for a moment. Another species somewhere deep inside the cosmic web, realizing for the first time that their galaxy is not alone. Perhaps they too feel that strange mixture of awe and loneliness. Perhaps they also sit quietly beneath alien skies trying to emotionally process the scale of existence. Or perhaps intelligent life is extraordinarily rare. That possibility remains equally haunting. The universe may contain countless civilizations, or almost none. We genuinely do not know. And that uncertainty contributes to the strange emotional atmosphere surrounding astronomy. The cosmos feels simultaneously crowded and empty. Galaxies fill space by the billions, yet the distances between them remain enormous. Life may emerge commonly, or consciousness may be one of the rarest things in existence. Right now, humanity still stands alone observationally. No confirmed alien civilization has contacted us. No undeniable evidence of extraterrestrial intelligence has appeared publicly, despite decades of searching. Which means that for the moment, Earth remains the only known place in the universe where matter became conscious enough to contemplate superclusters. That fact can feel lonely, or precious, maybe both. Now, Another reason people sometimes describe the universe in almost biological terms is because cosmic systems evolve through feedback processes resembling ecosystems in certain ways. Stars form from gas clouds. Stars create heavy elements. Supernova explosions enrich surrounding space. New stars and planets emerge from recycled material. Galaxies merge and evolve. Black holes influence star formation. Gravity continuously reshapes structure over time. The universe is not static machinery. It behaves more like an unfolding process of transformation, and human beings naturally associate dynamic, evolving systems with life. Still, there remains an important distinction. Biological life maintains itself through metabolism, reproduction, adaptation, and information processing in ways superclusters do not. Laniakea does not reproduce. The cosmic web does not possess DNA. Galaxies drifting through filaments are not cooperating consciously toward shared goals. Yet even without literal life, the universe still produces a feeling of strange vitality because everything moves, everything evolves, nothing truly stands still. Now, perhaps the deepest emotional question hidden beneath all of this is simpler. Why does the universe produce conscious beings at all? Physics does not obviously require consciousness. Stars could burn. Galaxies could form. Black holes could collide. The cosmic web could evolve silently forever without observers. And yet somehow the universe generated minds capable of wondering about it. That fact remains astonishing no matter how familiar science becomes. Tonight, somewhere inside one small galaxy drifting through Laniakea Supercluster, a conscious creature is lying quietly imagining structures hundreds of millions of light years wide. The universe evolved matter capable of contemplating the universe itself, and perhaps that realization softens cosmic loneliness slightly. Because even if humanity occupies only one tiny corner of reality, consciousness itself may represent one of the most extraordinary phenomena the cosmos has ever produced. Small does not necessarily mean meaningless. After all, neurons are tiny too, yet consciousness emerges from their relationships. Stars are tiny compared to galaxies, yet galaxies exist because stars gather together. Perhaps meaning in the universe does not come from size. Perhaps it comes from complexity, connection, and awareness. Now, one especially comforting thing about astronomy is how it quietly dissolves the illusion of separateness. Every human conflict begins looking temporary against cosmic timescales. Borders disappear from orbit. Politics vanish against superclusters. The night sky belongs equally to everyone. No civilization owns the stars. And inside Laniakea, Earth itself becomes one tiny shared home drifting through darkness together. That perspective does not solve human problems magically, but it changes their scale. Gently. And maybe that is enough sometimes. Maybe one purpose of astronomy is not merely to teach facts about galaxies and superclusters, but to widen emotional perspective until existence feels simultaneously smaller and more miraculous. Because the universe truly is strange. Gigantic invisible structures guide galactic motion. Dark matter shapes the cosmos silently. Superclusters may eventually dissolve through cosmic expansion, and conscious beings emerge briefly inside all of it, capable of asking whether the universe itself resembles life in some distant abstract sense. That is a very peculiar reality to inhabit. Yet perhaps peculiarity is exactly what makes the cosmos beautiful. One final thought begins emerging naturally from everything we have explored together. If structures this enormous exist all around us unnoticed most of the time, then what does it really mean to call any place home in a universe this vast? And so, after drifting outward through galaxies, clusters, dark matter, cosmic rivers, and the enormous structure called Laniakea Supercluster, we eventually arrive back where all meaningful journeys through the universe tend to end. Home. But perhaps home feels slightly different now. At the beginning of tonight's journey, Earth may have seemed like the entire stage of existence. A familiar world filled with cities, weather, routines, conversations, worries, responsibilities, and ordinary human life unfolding hour by hour beneath a relatively ordinary sky. Now the perspective has widened. The Earth became one planet orbiting one star. That star became one tiny point inside the Milky Way. The Milky Way became one galaxy drifting through the local group. The local group became part of a gigantic gravitational flow system inside Laniakea. And Laniakea itself became one thread among countless others woven through the cosmic web stretching across the observable universe. At every step, the universe expanded, and at every step humanity became smaller physically, yet somehow more connected emotionally. That is one of astronomy's strangest gifts. It reduces our importance in the most comforting way possible. Because once the universe becomes large enough, many of the things that dominate ordinary human anxiety begin shrinking naturally into more manageable proportions. Arguments, embarrassments, deadlines. The strange thing you said 5 years ago that your brain insists on replaying at 1:30 in the morning for unclear reasons. The cosmos quietly places all of it into perspective, not because human life is meaningless, quite the opposite. Human life becomes remarkable precisely because it exists at all inside a universe this enormous. Tonight we explored structures so large that light itself requires hundreds of millions of years to cross them. We followed galaxies drifting through invisible currents shaped by dark matter. We stood mentally beside clusters containing thousands of galaxies, while discussing forces capable of pulling entire regions of the universe together. And somehow, somewhere inside all of that, conscious life appeared. The universe evolved matter capable of asking questions about itself. That remains astonishing no matter how many times you hear it. Right now, every person on Earth is travelling together through Laniakea, whether they realise it or not. Every city, every ocean, every sleeping child, every late-night worker, every person quietly listening beneath blankets somewhere in the dark. All of humanity floats together through the same cosmic structure. The divisions that feel enormous during ordinary life begin looking surprisingly temporary from this perspective. Countries disappear from orbit. Politics vanish against superclusters. The night sky belongs equally to everyone. And perhaps that realization matters now more than ever. Because human beings often feel isolated from one another, despite sharing the same small world, drifting through the same enormous universe. Loneliness has become strangely common in modern life. People sit surrounded by millions of others in crowded cities, while still feeling disconnected somehow. Technology connects continents instantly, while emotional distance sometimes remains enormous. And perhaps that is why astronomy can feel unexpectedly comforting. The universe reminds us that connection exists whether we notice it constantly or not. Physically, chemically, cosmically, we are linked to everything around us. The atoms inside your body were forged in ancient stars billions of years ago. The oxygen you breathe passed through forests, oceans, and countless living creatures long before reaching you. Gravity ties Earth to the Sun to the Milky Way to larger structures beyond it. Nothing truly exists alone, not even galaxies. Now, there is another curious emotional effect that happens when people spend enough time contemplating cosmic scale. The night sky stops feeling empty. For much of history, the darkness between stars looked vacant. But modern astronomy transformed that darkness completely. Every faint point became a sun. Every fuzzy patch became billions of stars. Every direction in space filled with galaxies extending farther than human intuition comfortably handles. The universe is not empty. It is overwhelmingly full of structure, full of motion, full of history unfolding across billions of years. And somewhere within all that immensity, life emerged at least once. Perhaps many times. We still do not know. Maybe tonight, somewhere deep inside another galaxy drifting through another supercluster, another civilization is looking upward asking similar questions. Perhaps they too discovered cosmic structure gradually. Perhaps they also realize their galaxy belongs to something vastly larger. Perhaps they sit quietly beneath alien skies, feeling the same mixture of awe and loneliness humanity feels while staring into space. Or perhaps consciousness is extraordinarily rare. Maybe the observable universe contains only a few scattered islands of awareness separated by impossible distances. That possibility feels lonely, yet even then, existence itself remains extraordinary. Because against overwhelming odds, the universe produced beings capable of wonder, and wonder may be one of the most beautiful things in existence. Human beings are fragile creatures in many ways. We worry easily. We misunderstand each other constantly. We panic over small inconveniences while drifting through cosmic structures so vast they barely fit inside thought. Yet we also create art, music, science, kindness, stories, and curiosity. We build telescopes to study galaxies millions of light years away. We invent mathematics capable of describing space-time itself. We sit quietly at night imagining superclusters while trying to make sense of existence. That combination of fragility and curiosity feels deeply human, and perhaps deeply beautiful too. Now, one of the most important lessons hidden inside astronomy is that scale changes perspective without erasing meaning. Sometimes people assume that because humanity is physically small compared to the universe, human life must therefore be insignificant. But size and meaning are not the same thing. A single thought occupies almost no physical space, yet thoughts can reshape entire civilizations. A tiny strand of DNA contains instructions for building living organisms. Small things matter constantly. Consciousness itself may be physically tiny compared to galaxies, yet awareness transforms the universe emotionally because it creates experience. Without conscious observers, beauty would exist silently. Stars would burn unnoticed, galaxies would spin unseen, superclusters would drift forever without wonder. Human beings give the universe a way to be experienced. That matters. Tonight, somewhere on Earth, perhaps you're listening while half asleep. Maybe the room around you has grown quieter. Perhaps the world outside your window feels calmer now than it did earlier. Meanwhile, the Earth continues turning beneath you. The solar system continues orbiting through the Milky Way. The Milky Way continues drifting through Laniakea Supercluster, and Laniakea itself continues flowing through the evolving cosmic web, all without needing your attention for any of it to continue. There is something deeply soothing about that. The universe carries on patiently. Stars burn slowly. Galaxies move gradually. Gravity shapes cosmic rivers over billions of years. Nothing hurries. Not really. Human beings often live as though every moment must be optimized constantly. Productivity becomes a kind of religion. Rest starts feeling guilty. Silence becomes uncomfortable. But the cosmos operates differently. The universe is patient. Entire galaxies take hundreds of millions of years simply to rotate once. Superclusters evolve across timescales so enormous that human history vanishes into invisibility beside them. And yet, despite all that slowness, complexity still emerged. Life still appeared. Meaning still formed. Perhaps we do not need to rush quite so much either. Now, before we end tonight's journey together, it is worth pausing for one final thought. For almost all of human history, nobody knew structures like Laniakea existed. Ancient civilizations looked upward and saw stars. Beautiful stars, certainly. But they could never have imagined the gigantic architecture hidden behind those tiny lights. And yet the structures existed anyway. Human ignorance never changed reality itself. The Milky Way still drifted through the local group. The local group still flowed through Laniakea. the cosmic web still stretched across the observable universe. Long before humans evolved, long before Earth even formed, the universe was already becoming what it is now. And perhaps there is humility in recognizing that reality is always larger than our current understanding of it. There are likely discoveries waiting ahead that will make today's cosmology appear incomplete too. Future civilizations may map structures even larger than we currently imagine. They may solve dark matter. They may understand dark energy. They may uncover truths about consciousness, space-time, or the origin of the cosmos that would sound impossible to us now. The universe still holds mysteries, many of them, and honestly that is comforting. A completely solved universe might feel strangely lifeless. Mystery keeps wonder alive. So tonight, as you rest somewhere on this small drifting world, remember this. You are living inside one of the largest known structures in existence. You're made from atoms forged in ancient stars. You're carried through space by cosmic rivers shaped by gravity and dark matter. You belong to a species young enough that it only recently discovered galaxies, yet curious enough to map superclusters hundreds of millions of light years wide. And despite the scale of the universe, despite the enormous distances and the strange loneliness that sometimes accompanies cosmic perspective, you are not separate from any of it. You're part of the story too, a very small part physically, but a meaningful one, because the universe became aware enough to wonder about itself through minds like yours. And perhaps that is one of the rarest things in all of existence. So wherever you are tonight, whether the sky above you is cloudy or clear, whether city lights hide the stars or darkness reveals them brilliantly, remember that beyond the atmosphere, beyond the solar system, beyond the Milky Way itself, the giant structure called Laniakea continues drifting silently through the cosmos. And inside it, on one tiny planet orbiting one ordinary star, millions of human beings are floating together through an ocean of galaxies.